Check, check, check. Yeah, yeah, yeah. Check, check, check. Yeah, yeah, yeah. Check, check, check. Yeah, yeah, yeah. Check, check, check. Wah, wah, wah. Wah, wah, wah. Wah, wah, wah. Yeah, yeah, yeah. Check, check, check. Yeah, yeah, yeah. Check, check, check. Yeah, yeah, yeah.
but this one is absolutely worth a rewatch or a watch
Hallo.
Ik kan hem muten hier als je dat wilt.
Ja, dat is goed.
Ja? Wil je mij even een seintje geven als je dat wil zeggen?
Ja.
Dan zet ik hem even.
Okay, that's on.
wat?
Goeiedag, hallo.
Ja, precies. Nu is hij dus unmute. Dus wat jij...
Fantastisch. Dus ik hem nu weer uit. Oh. Ik heb hem nu uitgezet, maar ik hoor mezelf nog wel. Of is dat een in-ear
start our on time.
Okay.
All right. Let me go get the lighting real fast. Need the lighting here. This one, I think we're ready to start. Yeah. Yeah, this guy will get that.
How do I pronounce Feinster. All right. Welcome.
Welcome to Rust Week. Thank you for coming very much. I guess you've got the mic now. All right, welcome to Rust Week. Thank you for coming. We're so glad to have you all here today. The two of us will be helping to run the proceedings today, I guess. I'll let you, James, introduce yourself first.
Hi, my name is James Daly. I run the meetup just down the road in Amsterdam for Rust. I work in trading and I'll be one of your MCs for the day.
Hi, and I'm Bart Massey. I'm a computer science professor from Portland, Oregon in the USA who's been doing Rust for a while, and we'll be talking to you later today about embedded. And so, yeah, good to meet you all.
Yeah. Just for your own information today, there will be volunteers in yellow t-shirts all around the venue. If you need any help with anything, any help with accessibility, or you need to know where to go, or you're confused, I hope that they can help you.
Yeah, there should always be somebody at the registration desk. If there isn't, when you get there, wait or look around, because yeah, we want to make sure that we take care of y'all while you're here. Please, we have a code of conduct, and we take it very, very seriously. Not just for this event, but for all the events associated with Rust Week. So please understand what that code of conduct is, and I know it goes without saying, but please do follow that code of conduct.
Yep. Just for your own information, there is a live stream of all of the talks that we have here today. If you want to find it, it's on the landing page of the Rust Week website. And if you want to share the live stream with some of your friends who couldn't make it here today, feel free to do so.
Yeah, and the talks will also be recorded, so they should be available soon after the event for those of you who can't make the for people who can't make the live stream. The Discord's been very active. Please go to the page or to the front desk, and you can find the Discord address. Join our Discord and join us to talk to each other. You know, we're having a lot of fun, but it's also a place to find help and meet up with people.
Yeah. Just for your own information, all of the talks will be held upstairs. I believe there's 3 different cinema rooms here, all in a row. And any socializing, drinking, or eating, please try to keep it downstairs. Just to keep the place clean and keep the hosts happy.
I'm afraid I'm already guilty of violating that, but now I know I'll try to do better. There are 3 tracks. The main track is on this side, Cinema 12. That's got a whole series of talks. There is the industry track on the right here, which has a whole series of talks. And then there's us, the ecosystem track, including the Rust GOSIM Spotlight, which I'm very excited about. Please do feel free to switch between tracks. I know you're in the best track now, but there are 2 other really good tracks that you can check out as well. There'll be a social at the end of the day, so please stay around and hang out and chat with everybody there too. This is a social event as much as it's talks, so please enjoy.
Yeah. Just so you.
Sorry, I should go some spotlight.
Go on.
Yeah. So GOSIM Spotlight is one of the things that will be presented today. I was the head judge for something called the Rust GOSIM Rust Spotlight, where we tried to select people from a pool of community nominations, really 50 or 60 of them, that would present work that is super cool and super innovative, but also not so familiar to the Rust community. And so we're really, really excited to bring those talks to you today.
Yeah. And I think just for your own information, on the back of your tag, you can find the Wi-Fi and the Wi-Fi password. Yeah, useful, especially if you want to nerd out and show somebody some great memes or what you've been working on or whatever. Yeah, and I think maybe just a special mention as well at the start. I think this year we're celebrating 10 years since Rust 1.0. So 10 years official of the language, which is pretty incredible. Can I get a quick show of hands for how many people here have been professionally developing in Rust? Cool. And how many of you have been here since 1.0? Is there any? Oh, we've got a few veterans in the room. That's great to see. Great to see.
Nice.
Yeah.
So how many of you, this is your first year or so in Rust? You're brand new to Rust. Welcome to you folks as well. I hope you'll find this as welcoming a place as I have over the last decade or so.
Yeah. Okay. I think it's time for us to get out of the way. Nobody's here for this part. Jos, he's going to be our first speaker here today. He's a game developer from the Netherlands, and he's been doing some really, really interesting work with Bevy, and I'm sure he's going to tell you some really cool stuff. All right.
I get to find out what a polder is.
Thank you, guys. Thank you. All right. Bit of a spoiler right there. All right. Is everything working? It's working. Just at the start. That's incredible. All right. All right. Hi, guys. Thank you so much for coming here. Yeah, I wanted to start out with a pretty interesting quote that I want to leave hanging over the rest of this talk. We are often, we can get a bit carried away in giving a lot of opinions and analysis. I'll give a lot of opinions in this talk. But it's important to remember that practice, it has the final word. Doing it yourself, and just seeing what works for you. Always keep that in mind. All right. Again, thank you all for coming. I'll be talking about Polders, a game I've been working on for quite some time now, using the Bevy engine. And so I'm Jos Veenstra. I label myself as a spatial software developer and a technical artist. I'm the co-founder of a small indie studio called Geofront, which is a Delft-based indie game studio. If anyone is here in the field of computer-aided design, building information modeling, or GIS, come talk to me. I love to pretend that I'm still part of those industries. So why should you care about this whole talk? The thing I want to discuss next to okay, so what do you do with Bevy? What do you do with Rust? Is this interesting phenomena, this joke that has been going around in the whole Rust community, which is that we design 50 game engines and 5 games for some reason. Why is that the case? Like, that's a question that I think I know the answer of. I'm not certain, but I want to see if we together can get to a clear answer. I must say that I don't want to, like, it's completely fine to work on game engines. Like, this is not a talk to bash on folks that love to just build game engines. I'm the, a huge user of all of that effort and energy. So that's the last thing that I want to point out here right now. But if some of you are in the room looking to build your game in Rust or looking to do anything else, like just a creative, artistic pursuit, and if you have found that you're struggling with getting that implemented in Rust, then this might be interesting for you. All right, a small little overview, but let me quickly get you started with some footage. I mean, we're in a cinema right now, so might as well show you a trailer of the game I've been working on. Let's see if this wants to work. Thank you, thank you. Yes, yes. I think it might be important to explain to you guys where I'm coming from. You might understand the way I operate from that point of view. For me, all of this started just by being a kid. And it started with shapes. I loved shapes. I loved, having, I had my whole room filled with Azure paintings. And I was doing a whole lot of origami. And yeah, I just loved all things geometrical, all things with a pattern. And it was no wonder that I then started to study architecture as my main occupation. As an architect, you're always questioning, like, why is the world shaped the way it is? Like, what's the shape of the world and why? Like, for example, this building right here. Hands for everyone who knows this building. All right, some of you. This is Falling Water by Frank Lloyd Wright, one of the most famous pieces of villa architecture in the world. And you might be wondering, like, if you were to design a villa, why would you build it on top of a waterfall? Like, wouldn't it be very nice to have it as a view, to wake up in your living room and then look at a waterfall? But for some reason, this architect decided to put it on top of the waterfall. Like, why? And why this shape? Why this layered system? And these are one of the many mysteries that you tackle as an architect. If you have the answer, please come talk to me after the talk. I can answer, but I don't want to spoil it. And also, if we're going out for drinks tonight in the inner city of Utrecht, you might be wondering, like, why is this entire city shaped the way it is? Like, why is it layered like this? Why are there? It would be very much handy to have, if a boat comes here and has a lot of goods, to have that, well, immediately on the level of the shops. Why did they decide to make this lower area? So yeah, shapes. But there's also a part of me that really wanted to get analytical, get practical. So after finishing my bachelor's in architecture, I started diving into the Masters of Geoinformatics, which has you looking at the land, the shapes of the world, and analyzing it and trying to replicate that in the computer. And then one day, I came across a little tool, a little game, a little toy called Townscaper by Oscar Stolberg. And I was absolutely blown away by this thing. It's seemingly so simple. It's just if you don't know it, it's just a sandbox environment. You can just build blocks. But by building these blocks, you explain something that's very hard to it explains something that's very hard to explain for most architects. It's city morphology that's encased, and that you try to, while you're building in this whole tool, you see how the landscape starts to form around these shapes. You've built a river, and now, okay, I need some houses next to that river. You start to understand why cities are shaped the way they are by just playing around. And at the time, I was staring at point cloud data from the Netherlands. And that got me thinking of could you use a game to tell how the Dutch landscape was formed? Can you actually, without saying a word, explain to people how things are the way they are, just because they experienced it as being logical inside of a game? So geography for autodidact. So I set to work. How to make a Dutch landscape. Well, being a geoinformatic nerd, I immediately thought of a terrain model as being the first major component of designing that. And I immediately had a question of okay, do I want to go for a strict grid, or do I go for a very free-form approach from, for example, a lovely game of Tiny Glade, written in Rust, by the way. I don't know if if you guys know that. Probably you do. The problem here, of course, is that this is a way too much of a Manhattan approach to a Dutch inner city. And this was, for my case, a bit too free-form. I wanted to almost force the player sometimes into designing the city in a way. And once again, Oscar Stolberg, the maker of Townscaper, presented me with the ideal solution, which is this Goldilocks zone of a grid that is particular. It's a binary, there's something on this tile or there's nothing on this tile. But the structure that it creates is quite organic. And you can see that a pattern like this is a very good approximation of how the organic nature of a city, an old city like the inner city of Zwolle, how that is formed. You can see those patterns. So how does one make a Stolberg grid? I looked back on how I used to design geometry as an architect, and I briefly also worked in the CAD industry designing something called parametric glasses. So these were glasses to fit a human's face perfectly based on the scanning data of a face. So you have all this nice software laying about inside of this visual programming language called Grasshopper. And I wondered, okay, this existing software, it looks nice, I can use this quite well. Can I use that to basically, kickstart this whole parametric, or this whole geometry journey? And yes, I could, but it was encased in all sorts of layers and layers and layers of software. I would have had to make certain parts run on the cloud, basically, on a server, because it just I wasn't able to license this or to decompile this in a way that I could use all these geometric tools inside of a desktop client-side application. And after a lot of fiddling, I came across the conclusion, I need to write my own geometry kernel. And with geometry kernel, I mean basically just a library filled with lines, points, triangles, intersections, and everything you need to make geometry automated. Basically, anything you need inside of Blender, except from the actual environment itself to click around in. And that created a huge grocery list of okay, yeah, I want irregular grids. And for this whole game, I want some asset pipeline, maybe some wave function collapse, if anyone knows what that is. And all sorts of questions, like which language to use, what engine, what ecosystem, what libraries. And it was just too much. The task is huge. And this led me to my first sort of major guiding light in this whole creative pursuit. And that's solve et coagula. So divide and conquer. Start very small. Start with the absolute basics and work your way up from there. For me, that was a way to, to get away from the endless complexity of what's the best tool out there, what's the best approach, which engine, what library. So do the simplest thing first. So I did the simplest thing that I could imagine, and that's to build a very tiny engine. It was sort of a 3.js clone inside of JavaScript, just raw vanilla JavaScript, no libraries, no modules or anything. And you can scan that thing. It's a great idea to, during a talk, to have some people staring at their phone. But if you want to, you can. And you'll see that there are a lot of web demos that are still online, I think, I hope. This was my way of just hacking around and getting a foothold in the whole world of parametric modeling and automating geometry, but without any tools, without any dependencies basically interfering. So I made some little cute demos. This is marching cubes, if you're familiar with that. And you can see me already trying out this sort of townscapery grid. And the question now becomes okay, this is fine, this is cool. Can we scale this up? Well, yeah, you could. But here the practice thing comes back into place. Practically, I couldn't find a way to really scale with this. I couldn't see myself building a whole game inside of working like this. So I needed something better. And what more than our Lord and Savior, Rust. And I get a lot of questions of why aren't you using Unreal or Unity? And for me, going to those engines gets me back to that whole thing I was using at the during being an architect, of having some tools, but not completely owning that stack, not completely understanding what's happening, and that biting you in the butt at some point of the development. And again, I can give you a lot of opinions, I can give you a lot of analysis, but this, in practice, this just ended up working. And especially the mono repos that Rust provides are just a fantastic way to basically do creative coding. So using a mono repo, and I found myself on a very good balance between getting the freedom to make whatever small code project you want, but then also being able to take the reusable parts of whatever demo you made and putting it into a reusable library to be used for a larger scale project. Bevy was my partner in crime in that whole adventure. Bevy is, let's say, it is the biggest game engine in the whole Rust ecosystem, and a fantastic way to just hit the ground running. What I really liked about it is that it really helps with the pain points of Rust. It really abstracts away certain parts that you go into when you design your own game engine, like reusing parts of or mutable access. And that led to a whole bunch of other programmer art, and me trying to recreate those same demos inside of Rust and Bevy. And that also led me to, with that whole ecosystem in place, I was finally able to really get a foothold and really build some proper geometry kernel. And I can go into the specifics of this, the polyhedron data model. But what I would rather, this is all under the hood stuff for if you want to really build geometry from scratch, then you will have to build something approximating a mesh. But this is a long story. I'll skip over that for now. What I especially want to talk to you about is that, what made this work? what led this project or me able to, do all of this without me going into the same problems. I can't read. Okay. Thank you. Thank you. Yeah. So I kept on wondering about this, like what makes this whole Rust world work for me instead of the game engines, instead of doing this all in JavaScript. And I think it's just a conceit of like, okay, I'm just gonna make it the dumbest, shittiest code that I can think of. Like I really think that was the way I could get over the hurdle of the 50 game engines and the 5 games, is that I was just able or just allowed myself to write shitty code. So I Control F'd in my code base of like, okay, where I'm looking for shitty code, so I looked up shit and I got like 10 results back. Here's some shitty stuff that I didn't really figure out, or it was like, okay, it's fine, let's continue. And of course, I'm presenting this as a bit of a joke, but I think this might, I think we don't talk about this enough in the whole Rust ecosphere. And this is where I'm gonna get really like architectural and cheesy. So Nietzsche came up with this idea, or he made famous this idea of what should great art contain. And to his mind, it always consisted of a struggle between two forces, the Apollonian and the Dionysian. The Apollonian is the art of order, it's the art of structure, of beauty. And the Dionysian is the art of chaos. It's indulgence, it's seduction, it is creative energies, but the more dark creative energies. And to Nietzsche, these two need to be in constant battle if you want to make good art. And I think this is the point that I'm trying to make. I think we do need more Dionysian Rust. I think we're doing a whole lot of work to make Rust safe and structured and very robust. But what we might be missing is that we need to counterbalance that with being able to just hit the ground running, just get it to work. Just, I don't care how you do it, I don't care what paradigms you use, just get it to work. Another way to put it is to basically think of it as investment. Like you can put all of your chips into safe, low-risk investments, or you can put them in high-risk, big payoffs investments. And I got this from a fantastic book called Anti-Fragile by Nissam Nicholas Taleb. And in that book, he basically he asks the question, is it better to be safe, or is playing it safe the riskiest move of all? And so I think that Rust and Bevy allowed me to, that created so much safety in the code base, so much structure, so much tools to do great things, that it allowed me to do disgusting things. It allowed me to do whatever I needed, knowing that I can refactor it always. I can always fall back on the structure and safety that is the foundation of this whole stack. So, getting back to the geometry. So with all of that Dionysian engine stuff in place, I was able to create a sort of decent looking grid based on the sequence as described by Oscar Stolberg, the creator of Townscaper. And the great thing about not just modeling this, but doing it in a procedural manner is that you can start playing around with, basically how it's all procedural. So you can be like, okay, now what if I generate or use the same script, but I start out with a donut, or I start out with a cylinder or a sphere. And that leads to interesting surfaces. So when you start turning this into land, you can see okay, if we use a flat plane, it starts to look like, okay, this is starting to approximate a Dutch landscape, probably, maybe with a lot of windmills. I don't think this is quite Dutch, but it is interesting, right? You just start playing around with your code, you start being like, okay, what if I just add all of this code, but I use it on a sphere? And wow, okay, interesting. We're now playing Mario Galaxy, I guess. And oh, wait, okay. Or maybe this is a bit weird. And do I want this as world? Okay. Um, okay. Maybe keep it flat for the Dutch game. All right. All right. Are you guys all still with me? I don't. What's the time currently? I have 6 more minutes. All right. All right. 15. Wow. Okay. I've been talking at a rapid pace. Thank you guys for keeping track. Lastly, I want to show you guys a little bit more about the game that was cooked up in this whole Dionysian manner. So this game that I've been creating is called Polders. It's a sandbox crafting game, and all the footage that you see is in early alpha. And the whole point of this game is to trick players into building the Netherlands. So all the mechanics, all the systems in place are all designed after a real cultural phenomenon in the past of the Netherlands. And that makes a player explore the way the landscape was created as they explore the game. And this is the sort of scenarios that creates, these little quaint Dutch towns. We have some villagers, some cows, a church. This is the main game loop. So you build things that produces a lot of products, like cheese, like your stroopwafels, like anything Dutch, basically. You trade that away, as you do as a Dutch person. You don't keep anything for yourself, you trade it away. And then that gives you enough resources to then start building more things. And the water is a constant ally and a constant threat in this whole scenario. Yeah, so as I was saying, I really want the player to experience how the land was shaped by culture and also by nature. And some ways in which we did this is by making the polders. I promised to explain the polder. So what is a polder? A polder is an enclosed piece of land that the Dutch have made over the years to basically create farmland out of the sea or lakes. And I simulate that in the game by giving the player not enough space and forcing them to basically create enclosed pieces of land that they will need to drain. But the land isn't drained by themselves. They will need to dig sloten, ditches, to actually transport all that water to the windmills. The player will also be kind of forced to build canals, because most of these buildings need to be reachable by foot and by waterway. And that leads you to building canals by default, basically. Some interesting thing I came across when researching for this game is that these knotwilgen, I don't know if you guys have looked at the Dutch landscape and noticed some of these trees. I hope you do after this talk. These are actually used to strengthen the dikes. I didn't know this. So the roots of these things actually keep the waterfront in check. And that's why they are always like planted in a row next side to these ditches. So we added that. So the waterfront, the dikes are actually strengthened by placing knotwilgen in the game. And the landscape is also changed by water. So in the past, the Dutch used to call the water often the water wolf, the terrible creature that can sometimes like take a bite out of your dike. These little like enclosed, these interesting pools almost, you might have seen them in the Dutch landscape. These are actually scars. This is scar tissue. When a dike breaks, there's actually the force of the water is so great that it actually creates this whirlpool, creating a huge sinkhole, which is almost impossible to fill up with a dike again. So they're forced to build around it. So everywhere where you see these lakes close to a dike, you know that at some time in the past, the dikes broke here. And people have defended themselves against it by building their farms on top of like small hills called terpen, which is also, of course, all allowed by the player. So currently we're working on adding some more exciting visuals based on like the old Dutch paintings. It's fantastic. And we're deepening the gameplay. We want to make some more interesting simulation aspects to it. All right. So what's the conclusion of this talk? And what's the conclusion of the question of like what, like the 50 game engines and 5 games? My answer was Dionysian Rust. I'm very curious to hear about what your answers are. But for me personally, it was just the allowance given to myself to be dirty, to just make the ugliest code imaginable, and trusting that with all the great libraries that have, you know, thought their systems really through, you'll be okay in the end. All right, a quick before we stop the talk, I want to quickly do a shameless plug. Like we really want to prove that it's possible to make games without like Unity or Unreal and create them in more interesting manners, and keeping the whole art of designing these systems alive. And for that, I can really use your help in supporting this game. So please do wishlist it if it seems something that you would be interested in. Or join our Discord if you want to see all the in-depth updates. All right. Thank you so much, guys. Mm-hmm.
Sure.
Okay.
Now, are there any questions? Please come to the front. And,
One thing real quick while they're coming up. Do keep in mind, we'd love to have questions now, but also the speaker will be available later. We'll have the social events, so please don't feel like your question won't be answered sooner or later.
Hi, I'm one of the Bevy maintainers. This is my day job to maintain Bevy, and I am beyond thrilled that people are actually making games with our game engine. That's the point.
And I completely forgot to shout you out. Alice, thank you so much for giving me the opportunity to speak here.
Of course,
I owe it all to her. So, and please also thank the Bevy engine for doing all of their amazing work. I wouldn't be here without it.
Yeah. So on that note, you've talked about how Bevy is great for TCS for making the parts of some of the challenges of less painful. What parts were still very painful for you when working with Bevy?
Yeah, I think the parts where I would like a bit more Dionysian-ness. Let's put it like that. For me, the biggest pain points right now, and I don't know if they're fixed. I'm on an old version, as happens with projects like this, is sometimes Bevy can still crash if you are using, for example, inserts instead of try inserts, and that's in the process hurt me. There might be ways to like circumvent that, and but in practice, most of the time when a crash like that happens, it creates no issue for the whole game. Something has been added to something that was already trying to be deleted, so whatever, we can just ignore it. So if, and again, I don't know if it's fixed, but if there were to be a flag of just like ignore everything that's not absolutely critical and accept any error that you know is not completely like frying your laptop, that would be fantastic.
So if you're feeling like you really want to take on an excessive amount of suffering, you could update to Bevy 0.16, where that was one of our major features.
Fantastic.
Fundamentally, we found that, man, we're crashing like way too much. We should stop panicking everywhere, and we should instead actually return results and then allow the end user to configure, hey, we have this unhandled error, how do you want to handle it? And so you can just question mark and pipe all the errors up and then not crash and instead just log them.
And this only shows like how much you guys are interacting with the community and truly like understanding what the pain points are. So thank you. Thank you.
No, I didn't.
This is a question from the YouTube chat.
Oh, look at
How
that.
do you keep up with Bevy versions, and do you always keep your Bevy version?
What did I just talk about the Dionysian part? Like, no, I should be updating, but you know, it's hard to if you're in a sprint of like, okay, I want to show this to a publisher like tomorrow or in 2 weeks, it's sometimes hard to permit yourself to be like, okay, let's update the engine, because it's I'm also using a lot of custom shaders. I know that those parts change a lot between versions. There was one update that really took me a while to reconfigure and made me sort of kind of scared. And besides that, Bevy, I'm now using Bevy 0.12, and they decided to use the little cute planet thing as the logo of that update. So I also feel sort of obliged to still be in this version. No. You don't want to know.
What I'm wondering is how you, because Bevy right now has tons of many features, but not a lot of discoverability, because a lot of things are quite hidden under the surface, deep down the ocean of the docks. You'll find observers, which are a rather new feature. There's little videos about it. If you want to learn how to use them properly, you'll have to dive into examples, open source code bases on GitHub, and see how other people do it without video tutorials. How did you learn to do any of this?
Very good question. Yes, and I also stumbled upon this. Sorry, the mic is on the.
Can we have your microphone for the next
Okay.
information?
Oh, I'm hearing it somewhere. I hope you guys don't. Very good question, and I stumbled upon this at the start as well. The way I got around that was basically accepting that I was, again, gonna write ugly code. So instead of like spending my time trying to deep dive and trying to understand everything, for example, you can see that in some of the examples there were a lot of like mesh manipulation things, of like scurrying meshes. And for me it was more cost effective to just figure out how to do that myself and build my own mesh class, basically, than to see how I can mutate vertices dynamically inside of the Bevy structure. So here I would also invite you to, and I know that this is a bit of a weird point to make, but I would invite you just try to figure it out and accept that it won't be perfect, it won't be the idiomatic way, but just see if you can somehow make it work, and accept that at some point you will figure it out. You will notice like, oh, like now, like, oh wait, they thought of this whole situation. Now I can like remove all these parts of my code. That's what I would recommend. So taking a Dionysian approach, basically. Does that answer your question? Or
Yes, it does. And if it does go wrong, then you can always refactor later.
sorry, could you repeat that to the mic?
It does answer my question. And as you said during the presentation, if it does go wrong or you want to improve your just go quick approach, then it's easy to refactor because of the nature of the safety.
Exactly. Yes. Yes.
We have time for 2 more questions.
I found that trade-off really interesting, where you have the full grid, which is very constraining, and the complete freedom. And of course, the game is all about constraints. I was wondering if you've given it any thought, where you allow that trade-off to the user, where the user of the game player, can choose in his world modeling what kind of grid he wants.
Good question. And this is definitely a stretch goal, where now that this is in place, like I think this is also one of the things that is interesting when you're developing a game, is that you can explore the design space of the game. That's almost like what you need to do as a game designer. So now having all these structures in place, that a user could technically choose whatever grid they want. Like I don't know how that fits into the whole let's people design the Netherlands as it was designed phenomenon. But I'm definitely exploring to open up all those generation options to the user now that all of this code is just running in real time at the user's side, which is, not what you see in every game. So yes, very good question, and I will definitely add that.
We have time for 1 more question. Anyone have one final question?
Yeah, I was wondering if there's any other like major libraries or other tooling that you used in the game and can recommend, or anything that you are maybe missing.
Any major tool? Well, there are lots of like little tools that you include as you need them. Like you need a clipboard, so you need this, you need that. But specifically, I wanted to stray away from that reasoning for the purposes of this talk, to be like maybe writing whatever you want to make. Maybe writing that is not a matter of choosing the most perfect library or knowing the most perfect library, but more just a willing of getting it done. And I think that comes first, and then seeing if there's something in the ecosystem that ties to that, what you're trying to make, is I think a secondary aspect to your vision, at least from my point of view as someone who tries to make art with an engine. Like, I can totally respect other approaches for very different projects, of course, but I don't want to shout out any module specifically for getting that across. So, but thank you for the question.
Thank you.
Yeah.
Fantastic. You have some buffer.
There's like, the talk only ends now. Now is question time.
Oh.
10 minutes early, so good job.
Wow.
Yeah, so thank you. First of all, let's thank the speaker very much. Yeah, it was amazing.
Thank you.
It was also beautiful. My question was, did you do all your own artwork for that?
Yeah, most of the art you see is my programmer art,
beautiful.
but I do want to give a huge shout out to Danielle, who's now actually like truly upping it with. Let's go there. Ooh. The artwork you see in the back, this stuff, these are paint overs of. Also, this is Ruisdael, a classical Dutch painter. And we made this is not AI, by the way, this is a manual paint over, to figure out if we can take that style, take that, the language that was used here, and see if we can translate that to a 21st century cute-looking interpretation of that same style. So I really want to make a huge shout out to Danielle, who's now also making these way more in line with 17th century Dutch architecture buildings. You can see the contrast right here, like my dumb little approach of what a house is. I was like a little kid, and then seeing like what an actual house looked like at that point. And
well, thank
so,
you very, very much. It was an amazing, amazing talk, and we really
Thank you.
appreciate it.
Thank you.
So we've got a little bit of time. If you need to go to the restroom, or if you want to switch sessions, you're going to miss out on good stuff. But if you want to switch sessions, this is the time to do it. We will start again at 10:25 when we will start the GOSIM Spotlight Talks. We'll have 3 of those talks in quick succession here in just a little bit. So if your question didn't get answered, Jos will be around, I'm sure, and you can absolutely ask them later. And yeah, thank you, everybody.
good question. Very good to now on stage learn. That all my problems have been solved.
Yeah. Well,
that was great. Thanks. Hey, Francois.
You want to come with me and watch the
Yeah,
talk?
definitely. Let me.
I think the trader things. All right. Thank you very, very much, everybody, for attending. This section of the ecosystem track is dedicated to the GOSIM Rust Spotlight. And I'm very excited as the head judge, whatever that means, of the GOSIM Rust Spotlight, to thank both GOSIM, the Global Open Source Innovation Meetup, FutureWay. Did you have things you need to say?
I'm sorry, but the organizer's judgment is that you can't sit on the stairs due to fire safety. So please go to another track if you don't have a seat. Yeah.
That's too bad. I understand, but it's too bad. So while we're working that out, and I apologize, I wish I wish everybody could see these. One thing to keep in mind is every one of these talks will be both live streamed and recorded. So you can absolutely, if you miss it out in person, pick it up as it goes or pick it up later. I'm sorry that the crowding is the thing. It's exciting to see this many people here. So what I was going to say, so GOSIM Rust Spotlight, sponsored by the Global Open Source Innovation Meetup, with special thanks to Sid Askery of FutureWay and Huawei for funding a lot of this. We put this event together, and special thanks to Jane Lusby, who did a lot of the organization work. I don't know why my name says head judge, and to the rest of our judging team, who you should look up. But anyway, having said all that, the idea of GOSIM Rust Spotlight was to find Rust projects that are fairly new and very innovative, but that the Rust community hasn't seen yet as much. We want to give some exposure to things that we thought were really, really exciting. We had 55, I think, nominations, and they were all 55 great. I wish we could have given all 55 people a chance to speak, but we picked 10 that we had room for, and I'm very excited to present these people to you. So thank you very much to all the people who made it possible. We're going to start with Gu Haobo, who is going to talk to us about a subtopic that's very, very dear to my heart. For the first time in history, really, we don't have to accept what manufacturers give us in terms of keyboards. We can make our own very practically. And so Gu is going to talk about keyboard firmware. So thank you very much.
Thank you, Bart. And today I will talk about ARMK, which is a keyboard firmware written in Rust. And about me, I'm Haobo, and I'm working as a LLM researcher. But in my spare time, I mostly write embedded Rust, and I'm also a keyboard collector and creator. So now you know why did I start this project? Because I like building keyboards and I like writing Rust. So the first question is, what is the keyboard firmware? In one word, the keyboard firmware is the software running on the microcontrollers in your keyboard. It reads the physical keystrokes and converts those physical keystrokes to the digital report and send the digital report to your computer. It sounds simple, right? It was simple in about maybe 10 or 20 years ago, but now the keyboard firmware becomes a very, very complex embedded software because many features, the key processing features and the input devices are added to the keyboard, such as the touchpad, the trackball. So you might hear about QMK or ZMK. Both of them are written in C, and both of them have a long list of the feature set. So those more and more features and input devices makes the keyboard firmware a quite complex and the modern the embedded software. So before introducing ARMK, I want to talk about the embedded Rust ecosystem. This diagram is it describes the embedded Rust ecosystem from my own understanding. As you can see, at the bottom there are common hardware peripherals like GPIO and common protocols like I2C. And in Rust, we have embedded how on it. The embedded how is actually a set of traits which describes the common hardwares. And based on the embedded how, we actually have two sets of middlewares. The first is the how implementation for the specific microcontrollers, and the second one is the platform agnostic driver, which is actually the users of those embedded how traits. And on the top, in the actual embedded software, the application combines the how implementation for microcontrollers and the platform agnostic driver into the final embedded software. That's the embedded Rust, how the embedded Rust work in my understanding. And in this diagram, ARMK serves as two roles. ARMK core is actually the platform agnostic driver, and ARMK also provides a set of tools which helps you to build your keyboard application. So this is ARMK core. There are three main parts of ARMK core. The first one is the input devices, which including the K matrix, rotary encoder, joysticks, and those input devices are actually the driver, the platform agnostic driver. That means you can use those input devices with any how that implements the embedded how traits. So the input devices are responsible for reading the user's input and convert the user's input to the events, the input events. And in the middle part, the event processors process all those input events and convert those events to the HID report. This processor part is actually the most complex and most difficult part of the whole project, because there are many advanced features, many K processing logics is here. But what is lucky is that we have decoupled the processors with the input devices by the processors are only care about the input events. So thanks to Rust's great testing infrastructure, we can easily write unit tests for all the processors, which makes the life much easier. And for the last part is the HID reporter. The HID reporter is responsible for communicating with the PC, with your computer via USB or BLE, which is the Bluetooth Low Energy. And fortunately, we have trace again here. For USB, we have Embassy USB, and for Bluetooth, we have BTHCI. In Rust embedded world, there is also a great Bluetooth host implementation called Treble, which makes writing the Bluetooth reporter much quite enjoyable. Yeah. And there is one more thing I want to mention is that the whole system, the whole framework is fully event-driven, interrupt-driven, and async-based. That means you don't have to manually write your code to put your microcontroller in the sleep mode or low power mode. Thanks to the Embassy framework, this is done automatically. That means if you don't have your keys pressed on your keyboard, your microcontroller is automatically in the sleep mode, which is very cool. So next I will introduce the ARMK application. ARMK actually provides many tools for creating the keyboard application. The first one is ARMKit. ARMKit is actually a command line tool which you can use to create your keyboard project from the keyboard templates. And to make it more easier for new users, ARMK has a easy and simple configuration system which uses Rust's ProCmicro. When building the firmware, the ProCmicro will read a config file, a TOMO config file named keyboard.tomo, and convert all those configurations of the keyboard to a final to the final working code. And that means you don't have to write any Rust code to configure your keyboard. All you need is one TOMO configuration. That's the ARMK application. And the configuration is simple, but actually ARMK has a rich feature set. For example, ARMK has great microcontroller support, such as ESP32, STM32, RP2040, NRF52, thanks to the great Rust embedded ecosystem. And ARMK has also the VAL support. VAL is a software that means you can change your key maps on the fly when the keyboard is running. And ARMK is also low power ready, wireless ready, and stability ready. That means you can build your wired or wireless stability keyboard by yourself. And the future, there is actually still a long to-do list of ARMK. For example, the RGB support, display support, and if you are interested with writing Rust embedded applications, I think ARMK is a good start project for you. Okay. Oh, that's all. Thank you.
So thank you. Oh, sorry. Hi. Go ahead. So thank you very much. That the bad news is we don't have time for questions on these ones. The good news is that Haubo and others who are speaking today will be downstairs in the exhibition area at a table that's the Rust GOSIM Spotlight table. So I'd encourage you, if you have questions, go on down there and ask them and check it out. That's an amazing project. Let's thank the speaker one more time.
Oh, thanks. And I also have some stickers and badges for you guys.
Excellent. Excellent. So
Okay.
Denis Bajanov is next. I apologize if I've mangled your name. And wants to talk to us today about performance measurement and how it could be better. This is actually what we talked about.
Very, very excited about. There we go. Microphone's live now. Yeah, so thank you for that. Oh yeah, still getting ready to go. So like I was saying before without the microphone, downstairs, GOSIM Spotlight table. Check it out when you get a chance. Many of these people will be down there and would love to show you what they're doing in more detail. You good to go?
Yes, I think so. Is microphone working? No, not yet.
Not yet. So it'll be a minute more. It's all good.
One, two. No, it doesn't work.
Just a minute. He's got it almost set up. Yeah. So.
Yeah, now it works. Thank you. Thank you very much. So first of all, hello everyone. I'm really glad that you attend this talk. Thank you very much. Also, big thanks to organizers, of course, and GOSIM Spotlight team. It's really nice to be here and speak to you today. So I'm really passionate about performance engineering, and Rust is really great language for that kind of work. But there is one thing that's still challenging in any language, like no matter what language you will use. Benchmarking is it's hard. And today I'll introduce you to a new way of benchmarking named paired benchmarking and a open source library Tango that I wrote that implements this idea in Rust. So let's start with very simple basic concept. How do we measure performance today? The idea is very simple. You have algorithm, you repeat it bunch of times in a loop, and then using some high precision system timer, you measure the time that this loop takes. That's it. You can do a lot of things on top of that, like you can measure mean, median, you can build confidence intervals, but the main issue I have with this approach is the assumption that performance will stay the same when you execute algorithm multiple times. And this is so wrong. There are a lot of reasons like why we cannot measure performance precisely. Like I cannot go like through all of them, but important thing is that those factors that influence performance, they span multiple system levels. It's hardware, it's operating system, it's runtime, and Rust still has very little bit, but still has runtime, like for example, allocator state, right? And all this leads to like a lot of silly situations when you cannot actually like it feels like you're chasing the ghosts, you know, you're trying to measure some like performance, like you see difference, but now it's not there again, like what's happening, right? So how do we tackle this challenge today? How we try to approach it? Well, today the approach is very simple conceptually. You control what you can, you randomize everything else. And you can do a lot of meaningful work using this approach. And frankly speaking, it's the only one. So the question is, can we do better? And yes, I believe we can. And better solution, I believe, is never run single algorithm in isolation. You always need to run two algorithms you want to compare on the same hardware at the same time simultaneously. This way, if computer has some kind of biases, those biases will influence both algorithms at the same time. And when you subtract one time from the other one, most of the common mode bias or common mode noise will be eliminated. So let me illustrate the point. So here you see two runs of some algorithm. It doesn't really matter what it is exactly. But those two runs were taken, like obviously same hardware, same everything, but it was several seconds apart, right? As you see, like, they don't look like each other, right? They kind of different. But if you will take samples that were close to each other, like for example, if you will plot all odd samples against all even samples, right? You will see something like that actually on a short-term scale, performance is very predictable, right? And even in situations where when we have some fluctuation, like blue line is a difference, right? So even in situation like here, oh, you don't see my marking. Never mind. So even in situations when performance is different, it is symmetrical. And it is important because it tells us that the source of this bias, it doesn't come from the algorithm itself, it's the environment. And it allows us to reason about performance and more specifically about outliers more rigorously. So one takeaway from this is, performance is like weather, I would say. So it's pretty trivial to predict how weather will look like in 15 minutes. Well, Dutch people will probably tell you that it's impossible here in Netherlands, but you get the point. Like, it's much easier than to predict how it will look like in a month, for example. So we need to leverage this fact somehow. And this is what Tanga designed to do exactly, right? How does it work? Well, you build two executables out of your project. You don't have to build them at the same time. But when you run benchmarks, you need to have them both at hand, right? Usually, those binaries are built from different branches from your version control system, but, well, not necessarily. For example, it might be the same branch, but with different compiler options or different, I don't know, like different libraries, versions of libraries, right? And each binary contains, well, your benchmarks and the runner itself. And the trick here is that on all major platforms like macOS, Windows, Linux, each executable is actually a hidden dynamically load library. So it's like DLL or SO or dilib. You can treat each executable as dynamically load library. So what it allows the runner to do, like it can load both binaries into same address space and orchestrate benchmarks in a way that they will be run simultaneously. There are some tricks to it, but anyway. So I think I have time to do a demo of how it works in practice, right? Do I? Yeah, 4 minutes is it's plenty. So let's do that. And to do that, I will mirror. Okay, so you see my screen, right? Let me make it a little bit bigger. So I pre-built, first of all, benchmark. I have very simple benchmark. What I'm doing is I'm generating 1 million numbers, random numbers, right? And then I iterating over them, add 1 to each number, and then sums it. That's it. Very simple benchmark. What I will compare it to is to adding 2 to this number. In both cases, it's immediate value, right? Nothing like, no magic here. So I pre-built those binaries just to save on time, right? There are 2 of them, sum plus 1, sum plus 2. So what I will do right now is I will run, let's run sum plus 2 and compare it to sum plus 1. I will give some options additional. I will explain it afterwards if you're interested. So let's see what's happening. So, let me make it a little bit smaller, like that. So we see 0.5% difference, but it might be a fluke. Everybody knows that, well, it's very small difference, right? So let's run it one more time. Well, it's still there. Let me actually run it in for loop in bash. Just to run it like 10 times, for example, 10 times. Like that. Done. And I will decrease time from like 1 second to half a second, just to make sure that the difference is stable. We can actually check, like we can swap benchmarks, right? To make sure that this is not like some kind of bias. So let's compare sum plus 1 with sum plus 2. We should have approximately 0.5% of speed up, right? Because like we're just changing to benchmarks. So you see, guys, how precisely we can measure performance if we really like build the measurement right. So this is my demo. So let me go back to slides real quick. How should I do it? Like that, probably. Yeah. Okay, so the outcome is that computers were really never designed to reproduce the performance. They were built to reproduce the results of computations, not the performance, right? But in order to like build the measurement right and run benchmarks in the right way, we can actually benchmark performance more stable and in more noisy environments, right? And this is, I believe, very important today in the context of cloud, for example. A lot of code is run in the cloud. So this is it for me. Thank you very much. I invite you to try it out. Like there's QR code to project page. Try it how it works for you, how it fits your workflow, and share your feedback. Thank you very much and happy benchmarking.
That was fantastic. Thank you very, very much. Our last talk is Manuel Grewald, who will be talking to us about a new addition to the standard library, which is always an exciting thing to hear about. So I'll let you set up real quick. I'm going to have to ask Dennis later why, but because that's a really, really cool benchmark and why. But yeah, very, very cool stuff. So we may be running 1 or 2 minutes late. We'll try to get you out of here as quick as you can. Again, if you have questions, if you want to talk to these people, which I would highly encourage, downstairs in the Rust Spotlight table. Yeah. I guess I should say now, because we really are running up against the wall. There'll be catering downstairs at 11 o'clock. And Ferris glitter tattoos downstairs at 11 o'clock, because those are awesome. And so that'll be when we'll have a 40-minute break, is after this talk, and we'll just jump right out as it's done, so we get close to time. You ready? Are you guys ready to go?
Yep. Test. Yep. Seems to work. Yeah.
Excellent.
Okay.
So thank you, Manuel, very much.
Sorry?
Do you have audio with your presentation?
Yes, it's my presentation.
Okay.
So.
You need this one.
Oh, okay.
The audio.
Yeah.
Wow.
Okay. Oh. Yeah. Thank you. Okay. So yes, welcome to my talk about a new feature of the standard library, our autodiff macro. So I generally care a lot about doing all types of compute stuff in Rust, so like high performance computing, machine learning, scientific computing. And one of the things which I was really desiring for some of those projects was automatic differentiation, and we now have it fully upstream, and I'm working on enabling it for nightly builds. So here's a small introduction on how that's going to look like. So first, for those of you who haven't heard before about AD, it's a feature which is mostly used for, like, for example, training neural networks, but also in a lot of other scientific applications like climate simulations. We had to do a couple of compiler changes for that, which I briefly demonstrate, and where we already talked about benchmarking before. So I'll show some of the performance features, which are quite interesting. So first, what is autodiff? It's a new macro which is really experimental. So even after building the nightly compiler yourself from source, you still have to add this autodiff feature. And then if you have a nightly build, can use the standard autodiff macro, which is something which you can just apply to almost any function out there. Whatever you've been written in the past, it doesn't matter if you use any dependency or any creates, if you define your own types, we should be able to handle almost all of that. Except if you write inline assembly, but I'll get to that later. And yes, so for those of you, a small refresher of what derivatives are. So if you have a really simple function, x times x, the derivative of that is 2 times x. You might remember, like, if you take the derivative of sine, you get cosine and so on. So we don't really care, of course, for like these small toy functions in real world applications, but that's just a demonstration. We are working on a compiler level, so we are able to handle almost arbitrary complex programs in reality. And now what you do is, if you apply such autodiff macro to your function foo, then you first give it the name of a new function which we're going to generate for you. So it's just magically there. You don't have to worry about where it comes from. Then you are able to specify a couple of parameters. So for automatic differentiation, there are different types of AD. It's forward mode, reverse mode. The question is just like, how many input parameters do you have? How many output parameters do you have? For neural networks, for example, you usually use something called reverse mode, so that's what we have here. And then in the case that you have more than one input and one output argument, you're able to specify, like, hey, for like which input to which output you want the derivative. We do support things like MPI, GPU programming, batching, partial derivatives, custom derivatives. So if you've been using autodiff in other languages, like for example JAX, you might recognize some of those terms. And yes, so once you've applied the macro on the compiler side, we're going to take care for you that this function bar suddenly shows up. You pass your input arguments to it, and now suddenly, out of thin air, we have some extra output. So instead of just returning one float, we now return 2 floats. The first one is just whatever output you've been originally computing. So in this case, x times x, but the new addition output is the derivative. So in our case, 2.0 times x. So you get 6 or 8 there. Now, how is it possible for us to have an autodiff macro in the standard library, which is actually like state of the art? The shout out for that usually mostly goes to LLVM, which is the default compiler backend of our Rust compiler. So whatever Rust code you write, the Rust compiler itself doesn't do most of the optimizations. We do a lot of checks to make sure that your code is correct, but at the end of the day, we're going to lower it down through a couple of different stages to LLVM IR and let just the LLVM framework take care of that. So shout out to them for most of the things. Another thing which we have to consider is on why AD is fast is, well, first, automatic differentiation is kind of complex. We do heavily rewrite all your code. We like duplicate your code size in reverse mode. We had a lot of data dependencies here and there. And if you think about it, compilers at the end of the day just also like programs. They run out of energy. Like if you give an input to a compiler which is too complex, you've seen compile times of the Rust compiler itself. They're sometimes a bit slow. In our case, it's even worse. Like if you start duplicating the code and add all of these dependencies, LVM will just run out of energy. So you don't want to wait forever. So that's something to also keep in mind. And with that being said, one of the pretty classic examples for AD is neural networks. So if you look at a neural network, like you have a couple of input layers, you have some hidden intermediate layers, and then you get an output, which in our case might be classification, like cat, dog, whatever. And I mean, if you just load a neural network, like initialize it from 0, that's not going to do much. So the interesting is how do we train a neural network? And that's where automatic differentiation comes in. That's where you like just implement your whole neural network, your inference in Rust, put the autodiff marker on top, and suddenly instead of just doing inference, you can also do backpropagation, which gives you all the gradient updates. So after running your neural network, you know how to update your weights for a little bit to get slightly better results. And under the hood, what automatic differentiation does, as I mentioned, it duplicates your code size. So now suddenly you run from the beginning to the end, and once you're at the end, well, you go back to the beginning. So you run it a second time in reverse mode. That's where the name comes from. And beyond that, we have something called a tape. So to compute derivatives, you sometimes need stuff from the input or like from the beginning of your neural network, which has already been overwritten. So we might either be able to cache it, we might be able to recompute it, but at the end of the day, there's extra work going on. So that's how AD is usually slow in languages, because you just have so much extra things going on. And the normal compilation pipeline for all other AD tools is, well, you have some C code, we write it to some different C code, and then let whatever compiler backend you have do the work. Now for us, it's a bit more interesting. We have the Rust compiler itself, which allows for LLVM, and since we are an LLVM plugin, we have full control. So what we do is we first optimize our LLVMIR, which we got from the Rust compiler, to make it as small as possible. Then we run AD on something really small and easy. So now we duplicate the code size, sure, but I mean, it's just some really tiny program which is well optimized. And then since we generate a new code where we do want to run another opt run, just like for good measurements, because the code which we as an autodiff tool generate, that code might not be optimized yet. So that's a completely different pipeline, and you can get it already through the Rust flags environment variable by passing -z autodiff equals enable. We have a ton of other interesting flags which you can check out, but that's the most interesting one which you need to enable autodiff. So you see we are still quite experimental. And yes, with that you get the new binary which can now run derivatives. Now, we've talked about benchmarks before, and I've obviously been running some against the classic competitors like C++. And one thing which is really interesting for us is, first I've been implementing it all in pure Rust. So we have an LSTM, which is machine learning benchmark. We have Gaussian mixture models, fast Fourier transformation, bundle adjustment, and an ODE solver. So quite a range. And we, in almost all cases, if you look at the dark red one, Rust is doing pretty well. Now I also have a light orange one, because once in a while when I talk to people in other languages, they come up with, well, Rust, why do we really want to use it for HPC, for scientific computing, for all of that? You have all these safety overheads. Like every time you want to write something fast in Rust, you have to write in an unsafe Rust, right? So just as an answer to those people, I've been writing it using raw pointers, so we have no bound checks, and we also don't have any interesting metadata, because the safety which you get from Rust is also interesting for our LVM backend, because we get a lot of metadata out of it. And you can see if you use raw pointer, we're actually so much slower in a couple of these benchmarks, like 2.5x or 10x slower. So just writing safe idiomatic Rust is usually the much faster solution if you care about automatic differentiation. And then there are a couple of things like fast Fourier transformation, where we're not fully there yet. The reason is just it's like a highly recursive algorithm where you keep splitting slices in half and then like shuffle elements around, so LVM at some point just loses track of where to do bounds checking. It's a really easy fix, just like instead of doing a swap, you do a swap unchecked, and suddenly you have peak performance again and you match C++. But I mean, that's just the one case where we are actually slower by having safe Rust, so that's something I cared about. And then we have some other AD tools. I mean, in C++ it's the same underlying AD tool. They have the same compilation pipeline. So if you add the right metadata by hand, which we on the Rust side we get for free from the compiler, then you can match our Rust performance. If you forget to add the metadata on the C++ side, then, well, you are out of luck. Then you also have as bad performance as the raw pointers in Rust. And yes, so the next steps, I was originally hoping to actually be able to give a live demo on Nightly Rust. CMake was in the way. Some of you have been probably fighting it before. So we are working on enabling in CI once we fix all the remaining CMake bugs. I hope that a couple of people are going to test it out. We already received the first bug reports, which I was really happy from people who really compiled the Rust compiler from source, which by the way is super simple. There are like 3-line instructions if you want to test it out yourself. Right now, as you've seen, we do modify the compilation pipeline quite heavily, so we have requirements like fat LTO, which are even worse for the compile time beyond what we already do, so we hope to get rid of that soon. And yes, there's another project which I'm currently working on in the summer, like starting in 10 days. And yes, that's for GPU support. We have 2 GSOC projects. So yes, thank you.
Thank you very much. That's super exciting. Cool stuff. So, yeah, it's break time. The catering's downstairs, like I said before. Go down, get some food, take a break, and then come join us again at, if I remember right, 11:40 when we'll have another talk and some more stuff.
Okay, perfect. We probably have it then. I can check with Bart afterwards. Okay. No worries. And the pointer is it like to use? Yes. Yeah. Yeah. So it's connected to this laptop, and you can click here. No problem at all. Thanks. Yeah. Maybe. Yeah. Just come over to us when. Maybe when the other talk is ending, and we'll give you. Do you want the clip-on mic or do you like to hold a mic? The clip-on mic. A1. Okay. Perfect. All right. All right. Have fun, man.
Ik hoopte dat jij dat manager was.
Nee, ik was bezig met de audio, want dat was wel... Maar jij was bezig met de deur, dus...
Ja, ik was de hele dag de tijd bezig.
We waren allemaal
nou,
druk
een beetje
bezig.
de gaten voor de zou ik zeggen. Zet weer een mooi glas neer.
Ja, volgende dan...
Ik zou hem hier vast gewoon neerzetten en dan ben je meteen klaar.
Ja, maar dan weet niemand of het nieuw of
ja,
oud
oké, dat is waar.
Oké.
And then like take the difference between that and start separate.
Hey, everybody. Are you ready? Are you comfortable? Okay. Our next speaker here is my wonderful co-host, Bart. He's a professor at Portland State University in America. And I'm really looking forward to hearing what he has to say.
Shall we introduce the sponsors first?
Oh, but before that, he's a good co-host. I'd like to make a big thank you to our two of our diamond sponsors here today, AWS, Amazon Web Services, and the lovely JetBrains. They're both been fantastic sponsors. They've given great funding and great support for this event today. So I'd like to thank them very much, and if we can do a little clap for them, that'll be fantastic. They'll love that. They'll love that. All right, Bart, over to you.
Excellent. As soon as the slides are up, we're ready to go, I think. Not that there's much to it. So yeah, while that's going, I'll say, hi, I'm Bart. I'm a Rust guy since soon after 1.0. I'm a professor at Portland State University in the in Portland, Oregon in the United States, and am very, very excited about embedded Rust. And this is going to be a talk that for some of you may cover very familiar ground, and if so, I apologize. But what I want to do today is talk about where we've come in embedded Rust, where we are, and where we need to go to really realize the full potential of this super cool thing. But before I do that, I want to put my acknowledgements at the beginning. I want to thank a bunch of people. I want to thank the Rust Embedded community. The Rust Embedded working group in particular has been amazing, and I am notionally giving this talk on their behalf, although any stupid thing I say was surely mine. Don't blame them for my talk. But absolutely gave me this opportunity to speak, and I'm very excited and grateful for it. It gave me the opportunity to do a lot of things that I wouldn't have otherwise got to do in the embedded space. I want to thank the Rust Week folks, because this is an amazing event. I want to thank FutureWay for their support, which has funded a lot of my work and has gotten me able again to do things I wouldn't have otherwise, and in particular has allowed me to fund a thing that run a thing that I'm very excited about called Rust Edu, which is a group intended to bring Rust education to academia, but also to industry and other people. If you are interested in that, I highly encourage you to check out our Zulip, or our website and our Zulip, and get involved. It would be fantastic to have you. So having said all that, I want to go ahead and really hit. Oh, sorry. Apparently I don't know how to operate a slide anymore. Let me try that again. I want to hit the Rust Evangelism Strike Force returns. I don't know how many of you remember this meme from olden times, but I feel like it's time to revive it. And in particular, I feel like it's time to revive it on behalf of the embedded squad, the group that are doing the embedded thing. I think that's where the action is, and where the action is going to be in a lot of ways for the near future of Rust. And that's the case I'm going to try to make to you today. So before we talk about what we're doing in embedded, we have to have the argument you always have every time there's embedded, and it's really frustrating, which is, what do you mean embedded? What is this embedded thing you're talking about? And it's really, really fuzzy. I want to be super clear. You know, I tend to use the famous Justice Potter definition of I know it when I see it, but that's obviously pretty unsatisfying. That computer on the lower left corner is my first computer, the Northwest Microcomputer Systems 85P. It had dual 8-inch floppy drives and 64K total between RAM and ROM. It was a 8-bit processor, and by the standards of the day, it was an awesome desktop computer. Now, of course, it's a tiny embedded device. The Kim 1 there in the middle is another one of these computers that I worked with in the early days, in the late 70s, that was a little 6502 with like a couple of K of RAM and no flash, you know, it wasn't flash yet, no ROM. It was, you know, a fantastic little embedded board. And then on the right is the Milk 5 Duo, which is a $5 board that has plenty of memory for running Linux and a TPU sitting on it. Is that an embedded board? I don't know. We typically talk about embedded being, you know, sort of very small form factor, whatever that means, so that it can fit places. We talk about it having limited resources, although these days not that limited. We talk about it being programmed, and this is, I think, the important thing, using bare metal code, which is, of course, one of those cool sounding things, but all it means is that I control, or can in principle control, every byte that sits on the computer. There's no operating system in the way. There's no, layers that aren't there because I put them there. And that's kind of cool. And they typically either run in that we typically write either bare metal embedded, or we write real-time operating system embedded. There's a whole interaction between real-time and embedded that we won't get into here. And so I'm driving things pretty low, and typically what I'm driving partly is pins, right? The wires that come right out of the chips and that I can use to connect to things in the most bespoke way possible instead of having standard connectors or interfaces. There's sort of standards, but they're very low level. And so, why is it that we're doing Rust, right? We got to remind ourselves sometimes. I think this is, to me, an important part of the message for today is that, we get obsessed with memory safety. Rust is the memory safe language. Well, yeah, it's the memory safe language, and that's super, super cool. Without a garbage collector, we can avoid all the footguns of memory systems. But, garbage collectors are nice too. And also, yeah, that isn't the thing, right? If it was just like some other language, but with a borrow checker, I would be a lot less excited. I listed a bunch of things that I thought of off the top of my head that Rust is, that other languages typically aren't, all of, or even a lot of. And it's a long list, right? Our type system is, certainly beyond, closer to the state of the art than most type systems of languages that are in common use today. Sure, we're not Haskell, but we are a thing. We have super nice modularity and composability. We take for granted a really solid module system, good notions of private and public, the ability to compose modules and then compose those modules into crates in a clean way. You shouldn't take it for granted. It's an important part of what makes Rust cool. We have a build system that is absolutely 100% civilized, right? It's a build system that's bespoke for Rust, but that we can use in flexible ways when building Rust things. It's got a crazy amount of cross-platform capability, which is super important for embedded. It is just, we love our cargo and stuff, and we should, because it's really important. We have, very convenient public package store, right? Crates.io is amazing. And the fact that I can go just grab stuff off a Crate store and the build system will do it for us and just make things work. How cool is that? We have a stupidly good backward compatibility story, right? We really do have the experience. I really do have the experience of taking code I wrote 7 or 8 years ago and just compiling it and running it again without any issues, concerns. That's kind of special. It's really kind of special. We have, absolutely crazily good versions of integrated tools. Rust, other languages obviously have formatters. They obviously have, dot comment tools. They obviously have linters. But ours are good. I mean, they're like really, really good. And the fact that in particular that we use our formatter and that everybody's agreed on the format of the language, whether they like it or not, that's kind of special if you're working in some other language community. And we have nice levels of support for compile time checking of parallelism and concurrency, right? We have great threads, but we also have async await, but we also have send sync and all this stuff that checks that your thing's gonna be right? No data races in safe Rust. How cool is that? We have an FFI that works really, really well in general for interoperating with other languages. And I could just keep going, right? You're all bored now because you're like, yeah, we knew all these things. But look at them collectively, right? Look at what we've built. And yes, the memory safety is great, but this other stuff's great. And, I always think of that, line from The Life of Brian. Yeah, but what other than that, what have the Romans ever done for us, right? I mean, it's an amazing ecosystem. And so the story we need to tell in a lot of domains is, there's a lot here and you want all of it. But what about embedded specifically? Because this is supposed to be embedded talk. What I'm going to argue is that this is where we're the most special of anything. Right now I'm teaching Rust Web full stack and I'm teaching Rust Embedded at my institution. And they're both great fun and they're both cool. And I would absolutely recommend Rust as the language of choice for writing web applications, just like I would recommend it as the language of choice for writing embedded code. But the difference is that for web apps, there are some other stories, right? It's not crazy to want to write your web app in Go. It's not crazy to want to write your web app in JavaScript, I guess, TypeScript. But for embedded, we don't have a lot of great choices out there, right? We have certain legacy languages, let's call them, right? I want to be polite about this. I'm sure there's some C++ people in the room, and we love you. Absolutely, we're not trying to diss your universe, but I have to say, right? We have to say out loud, I think sometimes a little bit, that Rust has an amazing story for embedded that's just unparalleled compared to the story that's offered by the alternatives. And that's the word we've got to get out there. And right now, I think people aren't hearing as much as they could and not understanding the full story in what they hear. Let's talk about where we've come, though, because, it's only been 10 years. And in that short amount of time, we've done some really, really, really cool things in the embedded space, right? 8 years ago or more. These dates I grubbed off the internet, and I hope they're roughly right. People can correct me later. I make mistakes. But roughly 8 years ago, this thing that was then called Real-Time for the Masses, and now is called Arctic, was put in place as a Rust embedded framework for writing embedded applications, and it was fantastic. About 7 years ago, the Rust Embedded Working Group was formed and made part of the nursery, the Rust language nursery. Jose Aparicio and those people did some amazing, amazing work in sort of starting to standardize what Rust Embedded would look like in ways that were really, really powerful in terms of getting things going. And that was, it was a long time ago, and yet it was only yesterday. It was about 7 years ago, I think, that Ferris Systems was founded, which is a very, very important player in the Rust embedded ecosystem. I'll have more to say about them later. And in particular, their release of Ferrocene, a almost complete subset of Rust that's been certified to the highest ISO safety levels so you can use it in stuff like cars. It's pretty cool and pretty necessary to what we're doing. And Embassy, it's hard to put a start date on it, but the first official release was really only, the full release was really only a year or two ago. And that is an amazing, another runtime system that takes advantage of async await to enable a really, really nice style of writing Rust embedded code. So we're moving fast. We're not moving recklessly fast, but we are moving fast and in a really, really positive direction. Compared to 2 years ago, there's way more options available and they're way stronger and better. And I think that's part of the story we have to get out there too, is that if you looked at Rust embedded a long time ago, you should look again for sure, because there's some super cool stuff that's new. But having said all that, I'm old enough and was involved with the X Windows system enough to remember when it was frequently declared the year of the Linux desktop back in the 90s, mid to late 90s. I had a hard time pinning down the original source of that quote, but I promise you it was everywhere. And it was a sad story, right? Because every year was going to be the year of the Linux desktop, and then it never really was. I'm presenting these slides on a Linux desktop. It isn't like it's gone away, but the market share is not anything like 100% or even like 10% right now. And we could be there too. There was a nice quote on the Embassy blog that clearly 2024 will be the year of Rust on embedded. And I was excited, and I hope that, but on the other hand, I've been here before. So we really, really, really have to understand that success is not inevitable. It takes vision, which so far we seem to have in abundance. It takes hard work, and a small number of people are putting in a lot of hard work on this stuff, and I would love to grow that pool. And it takes some luck, and never underestimate the power of luck. But what I want to do today is encourage you to think about how we can make sure that this comes true, because like I say, it's a necessity. How do we move forward? I'm going to have some boring slides without many pictures on them for a while. I apologize. But I really want to talk about what we can do in education to on-ramp people into the embedded ecosystem. Hopefully some of the people in this room on-ramp them into the embedded ecosystem. I want to talk about how we can advertise, how we can get our message out better of what embedded Rust has to offer. I want to talk about how we cover more of the space. We're already doing pretty good, but there's more we might need to do. How do we get stuff usable and then get it used, right? That's a question that I think is really important. And I want to talk about the organizational aspects. We've got as far as we have by having good organization and teamwork, and I think we need to even more as we go forward have good organization and teamwork. So let's just take these point by point a little bit. Obviously, as the representative of RustEdu, I am excited about the educational aspects. One of the things I've been doing for the last year or so is editing the Rust embedded discovery book for the Microbit 2, which is, I think, a really, really good on-ramp resource for checking out embedded Rust. And we're trying to make it better as we go. There's a lot of materials in the ecosystem that have aged. There's a lot of places where any one of you could jump in, learn a tiny bit, take on some writing, and really, really help out. And I think that's going to be really, really important, is bringing stuff up to date so that it all looks new and fresh. The course content is a thing. That's something I'm supposed to be doing, and I'm making some good progress on. We really need to have some pieces out there. The comprehensive Rust short course on embedded is amazing. TeachRS has some modules on it. The Ferris Systems training materials, which they're gracious enough to open, are awesome, and I can highly recommend them. There's a bunch of tutorials and books, some of them commercial, some of them open, that you can get access to. But what we really need to do is figure out sort of how we get that into a coherent single piece. That's kind of RustEdu's job that I would love to have you come over to RustEdu and help me with, so that we have a single product to deliver that makes sense. There's a lot of advanced, pro training in embedded for industry, but the path to get advanced embedded topics by self-teaching is a little rougher. The good news is that the embedded Rust working group Matrix and the related Matrix stuff on Matrix are places where you can go ask for help. We do absolutely have good contact and one-on-one, but we need to get more written materials and help this thing scale. We have a surprisingly good coverage in Rust. Almost whatever processor and whatever board you bring along, we probably can mostly already support it with out-of-the-box Rust without you having to do too much. That's an amazing story, because the world of embedded systems, unlike the world of big computer systems, is super diverse in terms of the range of hardware that's out there. And I'm not claiming we covered all of it, but Cortex-M systems, for example, ARM is a microprocessor standard, right, for those of you who don't know, and there are sort of three kinds of ARM parts. There's the A parts, which are intended for cell phones and stuff like that. They're real full computers and barely embedded devices. The R parts, which are very little known and are intended for applications like brake controllers, heavy industry stuff with concurrency and reliability constraints. And then there's the M parts, which is what every hobbyist is using. They're amazingly cool little microcontrollers, and those we've got pretty much. The R parts is newly active. Jonathan Pallant and others at Ferris Systems have demonstrated running Rust on a Cortex-R part. And that's an exciting milestone for us because combine that with Ferrocene and you've now got access to a bunch of markets that are really going to be important. Our RISC-V story is pretty good. I first started doing embedded Rust on a RISC-V board 5, 6, 7 years ago, something like that. And it was fine then, and it's even more fine now, no surprise. You may have heard a lot about the ESP32 expressive systems, and the ESP32Cs are a RISC-V part. The 32Ss run their Extensa custom ISA, and Espressif has supported are the first vendor to offer official Rust support. They are funding and supporting the development of the Rust compiler backend that supports the Espressif parts, and that is super, super cool. AVR, the thing that the Arduino runs on, the Atmega parts, that's working okay, I think. I've never tried that, but I've heard good things from people who have tried it. So we've got this space pretty well covered. One of the things that makes ARM easy and special and cool is that you can use something called system view descriptions, which are XML provided by the processor manufacturer to auto-generate Rust crates to support a particular processor. That's kind of cool, and we're doing a lot of that kind of stuff. We absolutely have the embedded HAL traits, which are crates that provide trait definitions for traits that you can use to write portable device code for your thing. That's been really, really super important. We really are heap optional. Honestly, if you have enough RAM for a comfortable heap, you probably are barely embedded, but maybe you do. In that case, you can use it. You still probably don't want to use the standard library because it's so big and so, sort of not fit for purpose. But you absolutely can get by without any heap, and we have good support for that. Or you can get by with a limited heap, and we have good support for that. I'm going to speed through a little because we're running toward the end here. I think uptake is a place where, in the motto of the Research Institute my wife used to work at, more research is needed. That was their unofficial slogan. And I think we need to figure out, we need to provide attractive low entry cost frameworks, and we've done that to some extent. We've got Arctic, which is amazing. We've got Embassy, which is amazing. We've got the Talk as an example, one of several examples of a real-time operating system written in pure Rust. We've got Rust bindings for other operating systems now. Things like Zephyr provide Rust bindings if you want to use those as your real-time operating system. So we have a good story there. We need to provide better hobbyist entry points. The MakePad people are here as usual and are doing something that's really cool. What we really need is to have an answer to the Arduino thing, which is what the C++ people use in, as a sort of an on-ramp for hobby developers who might start out as hardware people with little programming. I think we can do better, and I think we're starting to do better. We have the professional entry points. One of the things where we really don't shine, and we need a lot of help, is we don't measure as well as we could. If we need to spend more effort on understanding who's using our stuff and who's not using our stuff and why the people who are not using our stuff are using our stuff. And I think that's a thing we can improve going forward. Organizationally, like I say, I don't have enough good things to say about the Rust Embedded Working Group. Now, maybe that's self-serving because I'm sort of officially part of the Rust Embedded Working Group, but I think they're amazing people and the leadership there is cool. We have lots of institutional support. A bunch of different groups have stepped up and really helped, not just with funding, but also with organization. One of the things that's happening this week as we speak is that our relationship with the Rust project and the Rust Foundation is somewhat in flux. People are trying to decide how that fits together going forward. And so I would really encourage people in this room to think carefully about it and then advocate for what you want to see happen, because it's going to happen soon and make a difference. Why am I so urgent about this? Well, I mean, part of the reason is that I think this is where the stable Rust jobs are going to be to some extent in the future, the ones that are reliably there. AI is, and plus, you know, the new round of offshoring from traditional software producing countries to less traditional ones is happening really fast right now. And a lot of jobs, even jobs that would potentially be Rust jobs, are, you know, going away or moving. The embedded world tends to be stable in that regard. It's a place where we can kind of promise you a big opportunity if you learn this combination of hardware and Rust skills. But also, obviously, you know, security and reliability has got huge attention in the embedded systems and Internet of Things spaces. Things have gotten a little grim. I chose to highlight this bug. I'm not picking on anybody, but it was such a great demo a couple weeks ago. Warmable zero-click remote code execution in AirPlay protocol. What that means, in case you're not familiar with the lingo, is if someone a bad guy happens to get too close to your Apple IoT device that's running AirPlay with their radio, then they can run whatever code they want on your IoT device. Whoa. And so you think, well, yeah, but everybody's always saying blah, blah, Rust, blah, blah. Would Rust have really solved this? Look, there were 2 CVEs here, one that reported by Oligo. One reported a buffer overflow on the stack, and the other one reported a use after free. So yes, Rust would definitely have solved those, right? I mean, it's not a case where it's ambiguous. The current mitigation is you turn off AirPlay and hope. Last I heard, you know, maybe Apple's got a fix out by now for their host machines, for their Macs, but updating embedded IoT code is a nightmare. And I reckon there's still bajillions of IoT devices that are vulnerable to this attack and will be for the future. We need to do better. So here's what I'm asking you to do. I know, I chose this aesthetic on purpose. I hope folks will forgive me later. I need you to check out what's going on. If you're not familiar, check us out. It's really cool, and we're really friendly, and we would love to have you become part of our thing. Even better, if you feel like helping out in Rust in some way, I know most of the people in this room are up to their neck in helping out in Rust, but if you're not and are looking for a place to help out, help us. I promise you we have projects at every level where we can use your help and support. It's not hard for us to find that. Do support us with the Rust Project and Foundation. Make sure that, you know, if you're part of that, and some of you in here are today, understand this is a place where we need attention. And if you're not, encourage people to think about that. But of course, the most important thing, which is what I've been trying to tell you, is to spread the word. Just get the word out there about Rust Embedded. I think it's really part of our future, and I'm really excited to see it go. So that is what I have for you today. I've left some time for questions, but I also will be around for the rest of the week. So bug me now or bug me then.
If you have any questions, could you please come to the front of the room?
Hello, Strike Force member from Call of Duty. You mentioned.
Oh no. There we go.
You mentioned the hobbyist path into this whole ecosystem, and you mentioned a professional path into this ecosystem. But I work at a small C shop that is neither hobbyists nor are they going to shell out for ferrocene or anything of that ilk. Do you think there's
It's kind of free.
Oh, it is?
Well, I mean, it's open source. Yeah.
But do you think there's a recommended or more viable path for getting a small C shop like that to take Rust seriously as an option and not just think it's overcomplicated? Or do you think it has to come from those other ends of the market first?
No, I think so the thing about embedded is that, yeah, there's a continuum, and I was pointing at the ends of the continuum, and you're right to call me out for that, but we understand there's everything in between. One of the places where we do need help, though, is that our materials for on-ramping people at your spot in the ecosystem are not as good as for beginners. And, you know, for experts, we have professional, you know, for people who want to work at industry scale, we have professional training that you can buy from various places, and that works great. For beginners, we have the Rust Embedded book that I'm working on that is the discovery book's pretty good, and I would highly recommend it. For people in the middle, we don't have as good of educational resources, but honestly, what I've found teaching this over and over again to college students is that you don't need that much Rust to get started, and you don't need that much embedded to get started. It's one of those things where just, the thing that you have to convince, I think, companies in your space to do is to give it a fair try. And that means having somebody who is either knows or is willing to learn a little bit of Rust, either knows or is willing to learn a little bit of Rust embedded, and sort of prototype and mess around, and has, I know that's a big ask for a small company, but be willing to prototype, mess around, see what works for them and what doesn't. My experience has been that people who stick with it a month, and this is one of those things that's easy to say, but people who stick with it a month will stick with it for a long time. That's about how long it takes to get super excited if you're poking at it for a while. So that's, I guess, my best answer. But yes, come help us. Come help us make it better for you folks.
Okay, thank you.
So I've done a bunch of hobby projects on Cortex M Blue Pill board.
Oh yeah, those things are cool.
I also have some of those Milk 5 Duos, but I haven't used them for anything yet because the Blue Pill is more familiar to me.
Me too.
But the way I am doing things is the same way that I've been doing things when I first learned Rust embedded a few years ago, which is using the HAL crits. And something that I found is that because it uses the type system for safety to make sure you have safe access to the registers and peripherals and things like that, you end up with these really unwieldy types that have lots of generics in them. And as soon as you can no longer rely on type inference, like if you want to make a struct or a function, you're not just doing everything in main. You have to write out all of those types yourself, and it gets really frustrating. So I wanted to ask if there's any developments in the ergonomics of this kind of stuff to make it easier for us to write this code without getting frustrated with really complicated types and complicated errors and things like that.
Yeah, I mean, you're absolutely right that people get frustrated with that. One of the things I'm guessing you found is that you've gotten used to it over time, that it was much, much harder in the beginning than it is now to deal with that. But it sounds like you're still having pain with it. It's always easier, I think, to provide safety and then provide escape hatches to get rid of it than it is to start without any safety and then try to provide escape hatches to add it. And that's been the approach of the embedded traits. So as you know, I think, you can always degrade, for example, a pin type into a generic pin type. And that is often the right answer, right? If you want or need that type safety, you've got it. But if you don't have it, just make it go away, right? And that is absolutely possible to do in the current space, and that's what I would encourage people like you who are still struggling with the type system to use. For those of you who don't know, there's this thing which is really cool but really frustrating in the Rust embedded space, where every pin on a microprocessor is given its own type. Literally, it's a unique type for that piece of wire. And you think that's the craziest thing ever. Why would you ever do that? Well, for example, that means that if I try to there's traits that say, the ADC can only be connected to these pins, and if I try to connect it to the wrong pin, I'll get a compile time error instead of a runtime thing that takes me 10 hours to debug. It's super useful, it's super safe, and it's super frustrating because these types get insane.
It's more that the Rust language, because it only has type inference for local variables, and if you want to refactor the code, and you have to figure out what type that was and type it manually.
Yeah, the biggest problem is that Rust's situation with globals is awkward, I think. And that's the place where you end up having to describe these types because you don't have a choice. And even if it's a degraded type, it may be fancy. So I think the answer is no. I don't have any great things to support. If you look at how the crates use these types these days, I think it's better than it used to be. But there's a lot of work to be done there. It's absolutely an area that good ideas would be welcome, I think. It's the best I got for you.
So
there is tons of firmware for the application processors, just for bringing them up and such. How do you feel about Rust embedded in that space, like Cortex-A and such?
Oh, I don't know the Cortex-A story very well. I probably shouldn't speak. I know that one of the things we just did in the Rust Embedded Working Group was combined the Cortex-A, Cortex-M, and Cortex-R groups into a single ARM group. and I think that's a really good thing, I think, because what it means is that we'll have a lot more cross-talk between people like me who don't understand A at all and, the people who do. But I think Rust works really good there, but I think the story is less interesting in some ways than it is for the M parts, because the A parts really are just, computers. they aren't. There's not that much that's weird about them, right? You've got virtual memory and giant RAM address spaces, and it's like, oh, okay.
Well, you need to get there first. And,
yeah.
We've been running a project for doing that for about 5 years now, using the embedded Rust traits actually.
Cool.
And that includes the Milk 5 Duo, if anyone is
Oh, that's super cool. I want to see your project. Drop me stuff afterwards.
Right. I'm sitting right there.
Perfect.
Again.
So you mentioned how Ferrocene enables the use of Rust in the automotive industry, but is there any work regarding certification for the aerospace industry? Because I imagine that'd be quite a bit more complex.
It is absolutely an active topic. I'm not directly involved in it, so I can't speak for the people who are, but I know that there is a group of people who are trying to get some of the aerospace certs right now as well. And I think the work, the ISO cert that they got for Ferrocene will make that a lot easier, because a lot of the conditions and processes are similar. But yes, it is definitely ongoing and definitely a priority for people.
All right, that sounds cool.
Yeah.
Thanks.
Any last questions?
No. Thank you very, very much, Bart,
Thank
for the
you.
fascinating
That was
talk
fun.
and the whirlwind tour of Rust Embedded. Fantastic. We have about 8 minutes until the next talk starts. Okay. Thank you very much for coming.
Hey everybody, can I ask you to take a seat and we get started? Alright guys, I still see quite a few empty seats spread around if you want to try and grab one. There's some here as well. Please don't sit on the stairs. The fire safety people will get mad at me.
I think it's fine if you have a few people. We have kept it now.
Okay.
Yeah, we have already done that.
All right. So I think we'll get started with our next talk. Our next speaker here is David Lattimore. He's after traveling the whole way from Australia to be here, so we really, really appreciate that. His talk is on Can Rust Revolutionize Linking 2. So here you go.
Thank you. So for the last year and a half, I've been working full time on writing a linker in Rust called Wild. So for anyone who doesn't know what a linker is, it's the program that takes the output from the compiler and combines them together into an executable that you can run. And why have I been doing this? Well, I think linkers are cool. I think maybe lots of people don't think that, and maybe me thinking that makes me uncool, but nevertheless, I think linkers are cool. And I'll try and convince you that they're cool. So why are they cool? Well, that they write the executables that we run. Unless you're running in an interpreted language, it's a linker's job to make the executable that you run of some sort. They get to decide within reason where everything goes in your executable. So they can lay out things. They can decide where each function is placed, where all the data is placed, within the constraints specified by the program, but they can lay everything out. And when linkers get things wrong, then often things tend to fail spectacularly, although they sometimes can fail in very subtle ways as well, which can be even worse to debug. They also give you an excuse for looking at lots of low-level details. So if you want an excuse to be able to learn assembly language and look at assembly language and learn about relocations and all the other technical things that go into linkers, then they're a great excuse to get your hands dirty with some of those kinds of details. And as software engineers, most of us enjoy optimizing things, but often there's no justification for optimizing things. But linkers are great because people really want linkers to be fast. And so linkers I've found to be a great excuse for playing with optimizations and trying to make things as fast as I can. So the Wild linker is written entirely in Rust. A bunch of the tests are written in C, but the linker itself is written entirely in Rust. It currently only supports Linux, and it is 64-bit only, and supports x86, AArch64, and RISC-V is in progress. I've been using it as my default linker on Linux for the last 6 or so months, and it works pretty well. Most of the time I don't even notice that I'm using it. It just works. It works for Rust code bases tend to be fairly homogeneous, so for most Rust code bases I've found that it seems to work well. With C and C++ code bases, which tend to have a bit more of a mix of unusual flags and compilation options, that they tend to be where you tend to hit oddities. But even those, a lot of those are working as well. The linker itself is very, very multi-threaded for performance reasons. And yeah, most of the commonly used features from linkers on Linux are implemented. But there's quite a long tail of less commonly used features that are not yet implemented. Things that, sort of the 1% and 2% of projects might use, but if you need them, then Wild wouldn't yet be suitable. But if you do want to use Wild and we don't support the features that you need for your project, it's definitely worth filing an issue to ask, because that's how I decide what to work on based on what people need. So the performance of Wild, I'll talk a little bit about the general performance characteristics. So for non-debug builds, Wild is very, very efficient. I put a lot of work into optimizing those. I've also put a bunch of work into optimizing debug builds, but so have the other linkers. And so if you've got lots and lots of debug info, it tends to be more constrained by memory bandwidth. You're just moving around potentially gigabytes of data, and memory bandwidth becomes very much the limiting factor. And it's often performs similarly to LLD and mold. Also, if you have enough cores, like if you have a Threadripper or a Ryzen or something like that, then compute efficiency becomes less of an issue. And as long as your linker is multi-threaded, then memory bandwidth becomes the limiting factor. And so in those kinds of scenarios, mold and wild tend to perform fairly similarly. However, if you don't have a system like that, like I do all my development on this laptop here, and it's only got 4 cores and 8 threads, and so on it, wild performs quite well. For ARM development, I've got a Raspberry Pi that I do development on, and so I'll now show you a benchmark for that. So this is, in the blue we've got LLD, in the orange we've got mold, and in the green we've got wild. So this is linking the clang binary. So it's a reasonably large binary, clang. From recollection, it's maybe like 180 megabytes, but I could be misremembering that. I haven't shown GNU-LD here. So GNU-LD is much, much slower than LLD, and if I include that on the chart, then it just messes up the scaling. So I just haven't included it. Usually when I'm benchmarking these days, I don't even bother running GNU-LD. I just compare wild against mold or LLD. In fact, most of the time when I'm benchmarking, I'm comparing wild against itself because I'm looking for regressions or improvements. Yeah, so that's where we're at with performance. So although the linker, I should have mentioned that my initial motivation for starting the linker was incremental linking, which I haven't yet done, but even without incremental linking, we're already seeing some pretty compelling performance. So I want to make Wild a fun project for people to contribute to. If you'd like to contribute, I'd love to talk to you about that. We've already got a few contributors who are contributing actively to it. There's plenty of challenging issues to work on, lots of deeply technical things that you can get stuck into. But there's also a bunch of less technical things. So if you don't want to tackle any of those more technical issues, there are easier issues. And I try to keep up a bit of a supply of good first issues that I've written up with instructions for how to do those things. It can be challenging at times writing those up, but I try to keep up a bit of a supply of them. And so if you can't find anything that you think is suitable, open a discussion on the repository and just ask for something to work on, or ping me on chat or something like that. So two of the main contributors that have been contributing lately have been Martin Liska and Mateusz, who have both been very actively contributing and helping lots. So I'll talk a little bit about some of the contributions they've been making. So Martin did the debug info support and also the port to AArch64, and is currently working on RISC-V support, which is getting close to being usable, or at least getting close to an initial version. So Mateusz has been driving getting the Rust compiler test suite to pass with Wild, which it does now pass if you run the tests locally. So there were various weird things we had to fix. So there were a few bugs that uncovered. That was really good to find those and get them fixed. There were also some weird things that the test suite does. So there's tests that pass these shared objects that are missing headers. I don't know where these shared objects came from. The actual object file itself is checked into the repository as far as I know. And so we needed to make our handling of those objects match what the other linkers do. And there's even one test that uses a linker script. So this is all now passing. We've also just started Google Summer of Code, and we've got a contributor from Kei Akiyama-san from Japan, who is a master's student who is going to be helping automate running of Mold's test suite against Wild, so that we can leverage Mold's test suite to find more issues with Wild and get some of those fixed. So once he's got that working, then the project will move on to investigating the failures and hopefully fixing a few of them. So as I mentioned before, with getting the Rust compiler test suite to pass, that required adding basic linker script support. So we've now got a bunch of the basics. So there's quite a lot of features that can go into linker scripts. A lot of them are fairly obscure, but we do have the basics working now. So you can map input sections to output sections. You can set the location at which sections should be placed in memory, and you can generate symbols relative to sections. So those are sort of some of the core basics that linker scripts need to be able to support, and we support those now. Another thing that I've been looking at recently is linker plugins. So these are necessary if you want to do link time optimization. The linker plugin is a shared object that's provided by the compiler, and it's passed via a flag to the linker. The linker then needs to open that shared object and make calls to it, and then the linker plugin calls back to the linker, and the two communicate. And together they take object files that contain bitcode or something like that and optimize it to produce new object files that then get fed into the link. So as you can imagine, this requires some interesting architectural changes to the way the linker works. So that'll be the main challenge of integrating this, is sort of fitting it into the model of the linker as it currently stands. The API was also, it's very C-like, and it looks like it was designed with a single-threaded linker in mind, and so fitting that into a multi-threaded linker can pose some challenges. So as I mentioned before, one of the original goals for Wild was to make it incremental. So the idea here is, if you make a small edit to your code, it'd be nice if we didn't have to redo all the linking from scratch, which is what most linkers do, and Wild currently does. So the idea is we would just detect what's changed, and suppose you've only edited one function, it'd be nice if we could just patch that function to fix it up, and ideally make linking very, very fast. So I thought I was ready to start on this last December, but we keep on finding other priorities, other things that have higher priorities. So fixing bugs, implementing various missing features, and trying to mature Wild a bit in terms of what it supports. And I have continued to think about the approach that I want to take with incremental linking. And so one consideration that I've been thinking a bit about is whether to do in-memory or on-disk. I'd originally planned to do on-disk. So the idea of on-disk state would be when the linker runs, it writes out a state file, and then when you rerun, it loads that state file up and does the incremental linking, then finishes again. I'm now thinking it may actually be simpler if I just kept the linker in memory while you're not using it. So the idea here would be when you go to relink, it would just connect to the already running linker and tell it to relink the program, which would then already have all the input files loaded except for the new one that's been updated, and it could then just check to see what's changed and update it. I may still eventually do on disk state because that could apply to different use cases, but I think for an initial implementation, in-memory is looking pretty promising. Another thing I've been thinking about just in the last couple of weeks is deterministic versus non-deterministic incremental linking. So Wild, when you run it normally, is deterministic. I go to a lot of effort to make sure that the output is deterministic. And I assumed that when I did incremental linking, I would need it to be non-deterministic in that you are patching functions and you don't want to go rewriting lots of stuff, because that's kind of the whole point of incremental linking. And so I assumed that I would make it non-deterministic. However, there's a thesis by Kai Nastinsky, sorry for the pronunciation, which talks about deterministic incremental linking, and in fact prototyped something like that with LLD on Windows. I don't think it was ever merged, but they prototyped it and got some interesting results. And so that's now another thing that I'm giving some thought to. Whichever approach I take, the priority will be on reliability and simplicity over always being able to incrementally link. So it'll be okay if we say only incrementally linked 95% of the time, and the other 5% of the time we fall back to a full link. We don't need to absolutely always be able to incrementally link. We'd much rather have something that works reliably and is simple to implement. So once incremental linking is implemented, another thing that I'm excited to have a look at working on is hot code reloading. So the idea here would be that it would build on top of incremental linking, but with various differences. So we definitely wouldn't want to be deterministic in the output here, because we need to leave functions. If there's already a function in a particular location, we need to leave it in that location because it could be currently executing. But the idea is, I guess I should step back a moment. With hot code reloading, the idea is that your program is running and you're changing the code, and those changes are showing up in the running program. So suppose you've got a game or a GUI running. You don't need to shut down the GUI or the game. You can just edit it and see the changes straight away. So yeah, so we need to leave functions where they are because they could be they could be currently executing. Again, I would want to prioritize reliability and simplicity over all kinds of updates being possible. So, you know, if you add a new dependency and you've got a large number of changes, then that's not the kind of use case we're looking at here. We're really looking at editing functions, maybe adding a new function, but not making large numbers of changes and then reloading those. So there may be also other limitations. So I may, for example, require that all functions go via the global offset table, because that would provide easier ways of updating, particularly on RISC architectures like ARM and RISC-V, which both have situations where if you're not going by the global offset table, it takes multiple instructions to reference an address. And if you're running and you update one of those locations but not the other, then that would cause problems. And so we can kind of punt on that issue a bit and just use the global offset table, which is just a table of pointers to things. So that means we can just update those pointers. So I'd like to finish by saying thank you to GOSIM for giving me the chance to come here, and also thank you to all of my GitHub sponsors who have helped make it possible for me to work on this kind of thing full time rather than having to go and get a real job. So thank you very much to those people. And does anyone have any questions?
If you have any questions, could you please come to the front of the room?
I'm just linker script standardization. Is it just the sort of thing where GNU LD set the standard and any other big linkers might add options? You just have to support what people use? Or is there a nice place where you can kind of look at the state of linker scripts?
So at least on Linux, GNU LD set the standard. So I imagine LLD just follows the same as what GNU LD does. I haven't looked at linker scripts on other platforms, so I don't know what the story is there.
Okay, so the first thing is a bit of a comment on what you said about the incremental linking, having like a daemon running in the background that you connect to keep state in memory. That would also be useful for non-incremental linking, right? Because I think it was Mold. They found that on some operating systems it takes a long time to spawn a process, and starting the linker process and then shutting it down adds a lot of overhead. Is that a use case that you've considered?
Yeah, so certainly the shutting down is an issue, and so in my benchmarks, Mold does take a while to shut down. Both Wild and Mold take a while to shut down, and so both linkers now both fork by default, and so both Mold and Wild. So I got this idea from Mold to fork on startup, and then when you've finished linking, the parent process exits, and the child process, which actually did the linking work, shuts down in the background.
Yeah, to hide that latency from the user.
Yeah, exactly. Yep.
And the other thing is, you said that link time optimization linker plugin is very designed with single-threaded linkers in mind. Do you see any potential for that API to be reworked in the future, as now multi-threaded linkers are becoming very popular? Do you think LLVM or something might have a new API standard for multi-threaded linkers for plugins?
I mean, it may be possible to. I'd have to look at the implement. I haven't looked at the way the linker plugin is implemented in GCC to see what it's like from a threading perspective. It may not be too hard without changing the API. It may be possible to make the implementation more suitable to multi-threading. Have to see.
Hi. So a lot of you've talked a bit about comparing with Mold, right? In the benchmarks you've used and in the various ideas that you've been inspired by. But you're still beating Mold, and that's really impressive. Can you talk a bit about where I'm sure that you've looked a bit at the architecture of Mold to understand how that system works and how you can compare it to your architecture. Can you go in detail a bit about where you found ways to beat Mold?
So believe it or not, I haven't actually looked at mold. I've tried to avoid looking at any of the other linkers because I didn't want to. I mean, I guess I didn't want to worry about licensing, you know, if I'm looking at their source code. And also I just wanted to come up with my own ideas and I felt like if I looked at the way they'd done things, I might end up just doing it that way rather than thinking about it myself and coming up with my own implementation. I mean, I know that mold is very multi-threaded, and my guess is that they're doing a lot more synchronization than Wild is doing. So Wild does very little by way of synchronization. I try to avoid sort of having lots of mutexes and those kinds of things, and instead just, you know, I rely a lot on scoped threads, and so and I've got quite a lot of phases. So rather than say having one phase that computes stuff and then when it needs to compute a shared value, sort of locking on that value and waiting for it to be computed, I would instead split that into two phases. So the first phase would work out what needs to be computed, and then the second phase will compute those things, and then maybe a third phase will go on to use those computed things. And that way you've got more phases, but each phase can operate without any sort of locking. It's just a bunch of things that need to be split up. So that's my guess, but I don't actually know.
Thank you.
You mentioned deterministic builds. I recently had some trouble with GNU LD with getting reproducible build with LTO enabled. So just wondering, do you have, like, what's your plan for that scenario?
I mean, I guess I would hope that the linker plugin would behave deterministically. If the linker plugin is not producing deterministic output, then there's probably nothing the linker can do. I guess it would depend on why it's non-deterministic, like where that non-determinism is coming from. But certainly, I'm not aware of anything in the API that would lead to non-determinism. Yeah.
Okay, thanks.
You may have already sort of answered this in one of the answers to the earlier questions, but I was going to ask about the link time optimizations. Often there is sort of the common approach is to turn off multi-threading in order to allow for better optimization for link time optimizations. Is that just because of the way that the API is written, or are there things that you can do within Wild that can better address those trade-offs that other linkers seem to have to deal with?
So at least in the LTO API that I'm implementing against, it's single-threaded in that you just call a function and the linker plugin does the LTO. So the LTO itself is very single-threaded. I guess going back to the question of the API being multi-threaded, there's probably not much. There's phases where it would be nice to be multi-threaded. The phase where it actually does the bulk of the work, it's hard to see how that would be multi-threaded, because I guess it depends. I suppose you could have an API where it split the work up, it figured out what work needs to be done, and then maybe a bunch of those bits of work could be done from multiple threads. So maybe that could be an option for changing the API to support multiple threading. But yeah, at the moment it is single-threaded. Yeah.
Thank you.
How can we as Rust developers switch to using Wild for like testing?
Yeah, so in the Wild README markdown on the Wild repo, there's instructions for, so you can download releases of Wild, you can install it yourself with cargo install or cargo bin install or those kinds of options, and then you edit your cargo config.toml to say use Clang as the compiler, use Clang for linking, and then use Wild as the actual linker, and then it just uses it for all Rust development.
Thank you.
Thanks for the talk. Just one question about the code reloading, because the way I usually see this happen is you build a shared library and then in the program, in the main loop or something like that, you unload the existing one and reload the new one. How are you going to handle this? Or I think you have something else in mind.
Yeah, definitely something else. So the actual the idea would be that your executable code is loaded and it remains loaded. It doesn't get unloaded, and any data that you've got loaded, like any global mutable state, is not being unloaded and reloaded. Like everything stays in memory, and you're just adding extra code into that already executable segment. So it's a bit tricky with executables, because executables on Linux get locked when you're running them, and so you can't edit it while it's running. That limitation doesn't apply to shared objects. So one option is to put all of your code into a shared object, not because you want to reload it, but just because we can edit the shared object while it's running without getting Linux's locking getting in the way. Yeah.
I think it's time for lunch now. We've gone slightly over. But David, thank you very, very much for your talk.
Thank you.
If you have more questions for David, I think you're going to be upstairs at the GOSIM section.
Yeah, I'll be up in the mezzanine area above, sort of where everyone is downstairs. So come and talk to me if you're interested in linkers.
All right. So yeah, the lunch will be downstairs right now, and if you have any allergies, please ask at the bar. There are staff there to help. Thank you.
Hi. Thank you.
Sorry. Just wanted to really quickly ask you, because the whole point of this is to make a really fast linker, right?
Yep.
Have you explored how much of an effect LTO and PGO have on your linker and file system?
I mean, I haven't got LTO working yet. Oh, do you mean LTO of the linker?
Yeah, if you
Oh,
compare
right.
the linker itself with LTO, and if you enable also profile guided optimization.
Test, test, test. Good? Okay.
Yeah, there's one. There's spots in the front as well. Could you put your hand up if you have a free spot beside you? Anybody? No? Okay. Okay, geez, we're full. You're a very popular man.
I hear that a lot.
Hey everybody, welcome back. It's great to see you. I hope you had a nice lunch. Before we kick off the afternoon's talks, I'd just like to give a quick shout out to Huawei and Z Industries. They're two of our premium sponsors for today. It's fantastic to have them on board, and the sponsors are really what make these kinds of events possible, and lets us have this sort of, showmanship. Our first speaker here is Kevin Boos. He's a tech lead at Project Robius, and he's currently the principal architect at FutureWay. And I think I'll just hand it over.
Okay, thanks. I'm not the only one, but I am an architect. Okay. Right, so today I'm going to talk about some work that we've been doing over the past 2 to 5 years, depending on how you count it. This is kind of the combination of 2 separate projects, MakePad, which is a UI toolkit that if you've been to Rust Week before, you're undoubtedly familiar with, and Robius, which I introduced last year at Rust Week, which is a companion, you can sort of say, to a bunch of different Rust UI toolkits. So today's talk will be a little bit different than talks that I've given in the past, in that I will dive into the code and actually show you how to write something like a real Matrix chat client, which I'll use as my primary demo. So before we get to that, I'll bore you with some overviews and front matter. So what is MakePad? What is Robius? What is our goal here? The goal is that you as an application developer can have a single code base, just one repository, that only uses one language, Rust, with no bridges, and it seamlessly works immersively on many different platforms by allowing you to deeply integrate with the platform-provided APIs. So we can have lots of nice screenshots, everything from a synthesizer on the top left to my chat client on the bottom right, and a bunch of different views of the same apps on different platforms. So that's kind of a quick overview. Let's talk about the background and the motivating characteristics of each project. So at a glance, what is MakePad? It's a high-performance UI framework that's written entirely in Rust for Rust developers. So it offers a custom UI design domain-specific language, which allows you to do some nifty things like a mixed or hybrid intermediate plus retained mode. It has shader-based styling, which is kind of similar to what you've seen in Shader Toy, if you're familiar with that, with built-in live reload of that DSL. It's very lightweight, very efficient, as you may have seen in previous talks. You can compile the entire thing, or the MakePad Studio, which is their IDE project, in around 10 seconds on modern hardware. Mine is an M1 series MacBook, so maybe 18 to 20 seconds for me, but that's still pretty good for an entire framework. Supports all the platforms that you would expect, and very recently, within the past several months, we've been working on supporting OpenHarmony as well. So then what is Project Robius? So MakePad was the UI toolkit for drawing, integrating with basic things like touch events and other system things that are required for UI. Project Robius aims to fill in those gaps such that you could access everything else from the platform that you'd want to beyond just the UI. So that would be things like accessing current location, bringing up a biometric prompt, and anything in between, not just hardware, but also the platform abstractions, maybe accessing application-specific local or cache data directories, things like that. Our secondary goal here is to make mobile a first-class citizen in the Rust community. I believe previously, not that this is any judgment on the project, but I believe that mobile has sort of felt like a second-class citizen, and there wasn't a lot of crates and infrastructure targeting writing an application on mobile. And you'll see that I can demonstrate our applications on iOS and Android, and they work just the same as they do on desktop.
And then kind of our underlying goal here is to bring two different groups together. One, we want to bring existing front-end developers over to the side of Rust, the dark side, and get them to use Rust and experience its benefits. And then we also want to allow existing Rust experts, all of our fellow Rustaceans here, to start actually developing applications in Rust, their beloved language. So I probably don't need to hammer home the points, but yes, the idea would be for developers to be able to leverage the robust and safe ecosystem that Rust has for high performance. They never have to deal with multiple languages or environments, no bridges, and you wouldn't have to write any sort of platform-specific code. So the two of these projects have been collaborating for the last couple of years, roughly, maybe slightly less, year and a half. MakePad itself has been under active development for over 5 years now, and today they just released their version 1.0, so that's exciting. I'm using they because I'm not in the MakePad team, but I do make significant contributions to it. But like I said, there's a lot more that you need to create an immersive app that runs on all these platforms and leverages the platform API. So the need for this fostered our joint collaboration, which has been ongoing for roughly the last 2 years, maybe 18 months. So both of these projects are fully open source and decentralized, just like most of the projects you see here. And everything is written entirely in Rust for Rust developers. So in the case of MakePad, there's no underlying web engine. We're not doing something like Electron. We directly use the native platform APIs, and the same is true for all of these Robius crates that you'll see. Excuse me. So this is a little bit different than I think the traditional application development style, where you have maybe the core business logic written in Rust, and then you have an additional set of libraries, or rather additional set of components that wrap that, and those are written in whatever the platform native thing is, like Kotlin or Swift. So just a little bit more boilerplate before we get to the code. What are our goals? So number one, we want to achieve feature completeness across the entire stack of anything that can be considered under the umbrella of application development. So that means a full set of widgets, support for themes, internationalization, localization, all that good stuff. We're still quite a ways away from this. There's quite a lot left to do. We want to be able to offer the application developer access to deep system integration, such that they can use platform features without any platform-specific code. And then we also want to allow them to easily build and package and publish those app bundles for the apps that they write using these tools. So I think that's pretty self-explanatory. In addition, we want to, eat our own dog food here. We want to create some apps using this framework and show that we can create beautiful, polished, and performant apps with nice code. And I'll show off, hopefully, a good example of that shortly. So here are some of the examples of apps that we've already written. So internally, MakePad has an IDE called MakePad Studio, which I briefly mentioned. That's for desktop. Today, I'll show off the Matrix chat client called Robrix, which I've written, which runs on all the platforms. And then we have a variety of other projects. One particularly cool one is called Molly, which is sort of like LLM Studio, but in Rust. And it allows you to run local LLMs and cloud-based ones on your desktop platforms. So the main idea here, again, our top-level goal, I guess you could say, is if we make a really good app, we make a really strong case for app dev in Rust, which benefits everyone in the community. Okay, so one of the things, I'll probably skip through these just to get to the code shortly, but one of the things we want to do is create a reference design for the full stack of system components needed to actually make one of these apps work. So of course we have the UI toolkit pictured, we have the concurrency management libraries, which we're working on, and the platform abstractions, which is kind of my main focus these days. And then all of these integrate nicely with the underlying platform. So for an app like Robrix, a relatively complicated Matrix chat client and more, you can see there's a bunch of different components here that we need to develop and that need to work nicely with each other. So far we have made Robrix sort of the driver for which things we prioritize implementing. So I've made a lot of contributions to MakePad in order to get it up to speed such that we can actually implement the various views and features you'll see in Robrix in a second. And the dog fooding has led to, I think, a nice path forward. So this is just one example. There can be many different structures for different applications, of course, but that's kind of the overall high-level diagram that we'd like to strive for. So all right, without further ado, let's get to some demos. I think I have to kill the slideshow to stop the mirroring. Okay, so, oh really? Oh, that's irritating. Sorry, let me unmirror again. Mirror. Okay, geez, I'm gonna have to do that every time. Okay. So this is Robrix. Robrix is a matrix chat client written 100% from scratch in MakePad and using Robius components. So when you first open, you get just a basic welcome screen. Now this is my actual personal account, so hopefully there won't be anything bad that you guys see. But yeah, you can see you get nice performance scrolling. We have a variety of different unique widgets. You can style things as nicely as you like. I think one thing that I really enjoy about Robrix is that when using Rust and MakePad, we have the ability for high performance. So we can do things like render dozens of rooms, dozens of chat rooms simultaneously. And using this dockable API, we can get a nice side-by-side room view, which is always something that I've missed in other chat clients like Discord and things like that. I hope the scrolling comes through nicely, but we can easily hit 120 FPS even with very demanding workloads and showing interesting dynamic or animated content as well. So let me just pick a few rooms, and I can show you off the dock and the resizability. So I can say, hi from Rust Week. And then we should see, oh, right, gotta go to the bottom, right? Okay, so what we're able to do here is, just the same stuff that you would expect from every chat client, but in order to get there was a relatively tedious process. So this is roughly maybe a year and a half of development, primarily on the frameworks layer. So the idea is the next person to implement something like this would then only need maybe a few months. So hopefully that will come true for whoever decides to try out an app motivated by its talk. So another thing that I've mentioned a lot is the support for multiple platforms, right? So in order to do that, we need to have sort of an adaptive view that changes to your screen size. So let me show you. Hopefully this will, is that working? Okay, yeah. So when you get to a small enough point, we're now at a mobile view, which is what you would see on iOS. So I can bring up my iOS simulator. This is the exact same app, no platform-specific code, nothing particularly different between the two other than the view that's chosen. And you can see there's sort of a different type of interaction. And we're able to reuse widgets very nicely across the two. So let me just click on one here. And you can see, I can give one example of something that's interesting in different platforms. So on a desktop platform like macOS here running natively, if I wanted to do some action like edit or reply to a message, I would right click. If I want to do the same thing on iOS or Android, of course you would long press, right? So that sort of abstraction is there, and the underlying infrastructure to make that happen is part of what I'll show off today, in addition to the actual code for this application. So yeah, that's Robrix. That's what you can do with MakePad and Robius, and there are also some other things we can do. I can give you one quick example. It's not going to be massively impressive, but I can show off the location here. And okay, yeah, that was instant. So this is using the Robius location crate, which abstracts access to your geolocation APIs across all the different platforms. So with this on macOS, you do have to have an actually fully installed version. So this is one that I've installed, as you can see here, running as a properly installed native app. So I'll go ahead and send that, and then here we are. And with other Robius crates, you can get interaction with opening different default system applications, like your browser, or in this case, I'll go ahead and open Apple Maps. I've actually never done this before. Let's see what happens. Okay, there we go. So we have that deep platform integration that you would expect from something, as if you wrote this app in Swift, but it's purely in Rust. Is that the right location? Yeah, sure, we'll say it is. Okay, so right, that's Robrix in a nutshell. I think I've maybe spent too much time on that. Let's go back to the talk, and then I will get into some of the code. Ah, darn. What is the shortcut for restarting? Is it like Shift F5? That's what I get for using PowerPoint. Shift F5? Yes, okay. So there's quite a few implementation challenges in creating a framework that is capable of writing an app like this. Of course, there's a lot of unexciting UI features that we had to implement, things like the infinite scrolling list, just the ability to show overlays, tooltips, things like that, a lot of initial UI projects they don't really want to focus on. So we had to get kind of this productivity business logic stuff out of the way. A major part of Robius and MakePad and every other project that is developing these UI toolkits spends a lot of time on exposing and abstracting the platform APIs and OS services, so that's sort of a given. Of course, we need to support complex multi-step builds that combine Rust. On Android, we might have Java. On Apple, we'll have Objective-C, and a bunch of different things that combine multiple pre- and post-compilation steps in order to actually create that application, which you then need to bundle, code sign, notarize, whatever it is, because a lot of this is required in order to access those platform abstractions on certain platforms. So geolocation, system notifications, as I mentioned, are things that require you to actually install a bundled app. And of course, we need to make all of this work nicely across completely wildly disparate platforms. We also focus very much on maintaining high performance in the face of high concurrency and asynchronicity. So in the case of a Matrix chat client, there's lots of stuff going on in the background, and we have a lot of interesting challenges there. I don't think I will spend too much time on those today, but one of them is that a bunch of different things can either only run on the main thread or require an async API, so we need to run them in an async context, or neither, and we want to run them in the background on a native thread context. And there's a bunch of different ways that we need to communicate with these different execution contexts. So I won't really get into this today because I want to show off some code, but this is one of the major challenges that we face, especially using an application SDK like the Matrix Rust SDK, which generally forces you to use asynchronous code. Okay, so now let's get into something actually fun. Okay, quick water break. So every time I see a really neat Rust app being demoed, I always wonder how it looks underneath the hood. What does the internal code look like? So that's kind of my goal with the remainder of this talk, is to go a little bit deeper than a visual demo and give you a feel for what the actual code looks like, and maybe kickstart your interest in writing a MakePad app. I will show off a few select components of things that you saw in Rubrics already, and hopefully that will inspire you. I have some explicit non-goals as well. This is not going to be a comprehensive tutorial. You won't gain expertise on Rust, MakePad, or UI dev, so I can't help you there. And this won't necessarily be the best way to do things. However, if this does inspire you and you do want to dig deeper, we have gone to great effort to set up a really cool MakePad demo room, which will open today behind Cinema 11 at 3 o'clock, and it'll also be around all day tomorrow. And then MakePad has a workshop on Thursday. I'm not sure if that's open, but if you're already in attendance, lucky you. Okay, so here are some things that I'm going to show off today. Just the basic view and widget structure, how you define widgets, how you make them work together. I'll dig down a little bit into the platform-specific code for MakePad itself, specifically something I added recently, which was support for native gestures, i.e. a long press or a long click. And then I'll talk about how we can have interaction between different widgets, no matter where they are in the widget tree, in weird and different ways. And then I'll show off real quickly how we can do something like access the location in a platform-agnostic manner. Okay, so bear with me here for a second. Okay, great. You can still see it. All right, so let's start with something really simple. I had shown this. Does that work? Great. Okay. Let me go to a test room. Okay. I had shown this little location view. So let's just study this one, right? Really simple, this little light blue background view. This is, oh, okay. Can everybody read this text? Is this okay in the back? Good? I can't see you, so I'm just gonna assume. Right, so this is very simple. It consists of just one line of text here, which is not changing. And then here, this is sort of, oh. That's blinding for me. Okay. Great, yeah, even better. So we have one line of text here at the bottom, and that corresponds to this. So this syntax here, here, I know what I can do. Excellent. Okay. So this corresponds to this label, and a label is just a plain view of unselectable text with a little bit of formatting. This is the MakePad DSL. basically this says instantiate a widget. It doesn't have a name. If we want to give it a name such that we can do something with it, for example, determine or handle an action or an event on that, we can give it a name like this, right? So you'll see I haven't given this one a name because I don't need to change it. It's just fixed text. This one here, I have given a name, and it starts with the default text of fetching the current location. And I have a little bit of formatting here. I want to move it, I want to move it slightly to the right, so I have a little bit of left padding. And you can define all these things differently. And then I have two buttons side by side. So previously, the context of this view was that it had a downward flow, which means each thing will come successively beneath the one above it as you define more and more things. But what if I want to have two things next to each other? Of course, I need to change the flow to something like right, or I can also have right wrap, where it'll automatically wrap to the next line if the things become too wide. But in this case, I'm okay with that. And then I define a subview within this larger location preview. You can see my cursor, right? Okay, great. A smaller subview that contains these two buttons side by side. All right, so one is the cancel button, and one is the send button. So that's basically just how you would define a simple view like this. Now you can get as abstract or as in place with the code as you want. In this case, I haven't done much special refactoring other than just taking this as a separate view and defining it here. I use, of course, unsurprisingly, a pub keyword, much like Rust, such that another view can include it as one of the constituent or child views within it. So in this case, I have an outer view, the room screen, which is including this view optionally. It's invisible by default, as you saw here. And then when I press this button, there will be a series of actions that occur that set the visibility to true. So yeah, this is not particularly unique but or interesting, but that kind of gives you just a very basic feel for what the DSL looks like. So the idea is here you're instantiating a view. If you want to connect it to a Rust structure, you use this syntax here, the double curly bracket, right? And then thanks to Rust Analyzer, we can jump to the definition. So this is basically just a simple wrapper around a view. And a view is just MakePad's very kind of basic default widget that contains any other number of arbitrary views. So then we have some data, some state that we want to keep within this particular view. Since it's a location preview, we care about things like the the coordinates that were retrieved from the platform and the timestamp. Perhaps maybe I wanted to show when you got that location so you could see if it was stale. Right, I'm not doing that in this view, but I could. And then, in order to handle events, I implement the aptly named handle event function, which basically gives me the option to query the DSL, query the views and the widgets that I created in the DSL above with special commands. So actually, yeah, so here's one example of that, right? So here I'm querying the button called cancel location button, which is what I named this particular button, right? And then I'm wiping the state and hiding this this view. So when I click cancel here, that's what triggers, because it'll be a series of mouse events that propagate throughout the system, and then we'll do a hit test on that button's area, and a lot of this stuff is abstracted away for you, but you can handle this this specific action within the code right here. And then I have a note that to actually handle the send location button being clicked, I can do that in a different widget. I don't have to do it here. I can do it anywhere else that I like. So in this case, it made a little bit more sense to do it in the higher level room screen view. So let me see, send location button. Yeah, so here's that code. Same sort of thing, where we're basically just doing a hit test hidden by this handy dandy clicked function, and then getting the current information and then submitting an asynchronous request such that a background task can go ahead and communicate with the Matrix SDK to send that current location as a room message. So I think that's relatively easy to follow. The idea here is that you can compose this and flatten it or structure it arbitrarily in any way that you want. You don't necessarily have to move things into a separate widget. As I showed here, it's actually probably the cleanest way to do that. But in this room screen, you'll notice this is many, many thousands of lines of code. So this is due for a refactoring in which we move more things into their own separate widget. But you don't need to do that. So it allows for, I think, relatively quick prototyping in that case. Okay, so that was just a very simple view. This particular view here. Can you? Okay, right. Let me go back to the slides and we'll look at the next thing. Okay. So you notice that that location preview pane was shown within the context of the larger context of a room screen, which is this particular view. So I'll give a little bit of a visual selection of each of the views and how we compose and nest them together. So this particular green outline box here is the entire room screen. You'll notice that it consists of a timeline, which is the list of messages, using the portal list widget, so that is the infinite scroll widget. And then we have a variety of different templates or other child widgets that can be displayed and added into the portal list. So we have a bunch of different things. We have a small state event, which is like somebody joined or left the room. We have a data divider, that's self-explanatory. We have a variety of different messages, things like the default message in red, which is text or an image message, or a condensed message, which is just the same thing without the profile information that you see here, right? And then we'll have things like reply previews, other sub-widgets within a message, your avatar username, and then of course the content itself, which is either richly formatted HTML content like we see up top, or just regular plain text. And then of course we also want to be able to show reactions here. And then it's kind of hard to see this example of a red marker to see who is to determine who has seen a particular message. And then at the bottom, the final thing that's included in the room screen is this input bar, which shows the location button that I previewed before, I demoed just now, a text input, which also allows for mentioning users, and then a send button. So this is how you would compose something like that. So if I were to show this off in a tree form, it would look something like this with a lot of things omitted just for the sake of brevity. And the things that I've shown so far are highlighted in blue here. I have shown some other things, but these are the ones that we focused on, so I'll get out of the way. Right, so the location preview, I can show everything because it's quite simple. It's just those things. And everything else, this is how everything else fits in. So then, the next question is, how do you interact between different widgets? Or from a background task to a widget? Yeah, how do you propagate state changes in data throughout the system, right? So let's say, let me go back. Let's say I wanted to, when I click this send location button, I want to do a variety of different things. I want to actually send the location, but maybe I want to do some other thing, like log a notification or save something to disk, right? For that, I can use what's called an action, right? So an action is a type of event, and I can show you this in the code, which is typically sent from widget to widget, and it propagates throughout the entire system. So let me start a new example with, let's actually start from the very lowest layer. How much time do I have left? Like 15 minutes? Okay. Let's start from the very lowest level of the long press, which you saw here, right? What happens when I physically press on something for a period of time? I get a gesture recognition event, which for iOS is handled here. So we've created a delegate. Let me see here. 5 minutes. Oh boy. Okay, I'm gonna have to move real quick. Okay, okay. So we'll go through this super fast. Basically, we define in Objective-C using the Objective-C syscrate a very simple delegate that waits for a gesture recognition state to occur. And then we send the long press up and we bubble it up to the rest of the MakePad layers, which eventually results in this long press event, right? So it's very simple, just the coordinates, the time, and in what window that occurred. And then if we want to actually handle this, as you may expect, we can go, oh, sorry. So there's a big old enum of possible events, and within this there are several different things. The one that we're looking for now is long press, which is here, and then we can do various hit testing on particular widgets to see if they were long pressed on. So in the interest of time, let me move back to the rubrics code. So we can search for long press, and in this case, this is the one that I want to see. So what I've done here is within the message widget, which is one of these, right? This itself is one condensed message. I'm doing a hit test to see if I've gotten a long press. If I do, I then go ahead and emit an action from that. And what that allows me to do is have this event, this action, be handled by a completely separate entity that has no relation to it in the widget tree. So again, what I'm doing here, just to clarify, I'm within a message widget here. You can see? Okay. I'm within a message widget here. I'm getting a hit test, and I am handling the long press event in order to emit an action. The action on the next event loop cycle gets propagated throughout the entire app, at which point any widget can handle it. So in this case, we want the top level app, the top level widget app UI instance to handle it, which looks like this, right? So if I right click, you can see I've put a kind of gray background over everything, and I have a highlighted content window that shows all the different actions you can take on that message, right? So if I click reply, another action will be sent back to the room screen that says the user selected reply, and then it will show this reply preview and focus on the keyboard, right? So in the interest of time, I am way behind time, so I apologize for that. But yeah, let's move on, or let me quickly show the way that the app handles this. So this is the top level app here. I am handling this by populating the message context menu here with show, and the contents are shown here. Right, you can see this basically does the whole thing where it determines which of the possible buttons, like for the various message actions, are visible and which ones are enabled. Right. When you click on one, I'm emitting that action again, and I am handling that back in the room screen, which I unfortunately ran out of time to show, which will then, perform whatever action you have, like showing the editing pane, showing the reply preview, or something like that. Okay. Well, I'm not going to have too much more time to do other cool stuff, but come see me or at the MakePad group, the MakePad booth for more information. So just real quickly, the current status of the project, as I said, most of the platforms are already there. Does it say 1 minute? Okay, geez. Most of the platforms are already well supported in both MakePad and Robius by our crates. We have Open Harmony as a new target platform here, in which we only have basic support for things like drawing simple UI stuff and touch input. As I said, MakePad recently had its 1.0 release. Here's a screenshot of MakePad Studio, which is an IDE that you can use to develop these things and have nice integrated hot reloading and a bunch of other cool features. Generally, the widget set is there of all the fundamental widgets, so you can take it and use it now. There's still some progress to be made, but that's where Project Robius steps in. So we have a bunch of different platform abstractions that we're targeting. Currently, this is our, yeah, there we go. This is sort of our state of the crates. Some of these have been added into MakePad, some of these have been added or implemented as standalone crates, and we'll continue to improve upon them. And then one thing I want to do the rest of this year is to test them deeply with other UI toolkits like Dioxys, Xylem, or eGUI, any of these projects, Slint. So we all sort of collaborate behind the scenes, and I think this is a great example of that. So I've mentioned some of the other roadmap items already, but real quickly, we just want to go ahead and continue to expand the widget collection and the support for different types of input events, namely app life cycles, like pause and resume on Android or something, and get all of that working very nicely with your application. We'll continue to work on adding more of those platform features, some of them that you saw missing or highlighted in orange, including support for Open Harmony. We want to improve build tooling continuously. We're using sort of a hybrid of our own tooling that MakePad has developed and Cargo Packager from the Tori community, and contributing to that as well. We want to publish these apps. I've published a release on GitHub for Rubric, so you can go and download that and try it out. But for iOS and other platforms that are a little bit more finicky and demanding, we'd like to publish that to the actual stores. And then, of course, documentation. So MakePad just released their 1.0, and they have some nice docs to accompany that, as well as sort of like a UI Zoo example that shows all the different widgets that exist currently. So you can go check that out. All right, so I think the main takeaway I'd like to leave you with here is that I believe that we can actually use MakePad and Robius together to develop a complex real-world app, as you hopefully believed, based on my demo with Robrooks. I think MakePad excels in enabling very high performance for demanding use cases, but maybe not so much in the case of a super simple quick start for a relatively simple, one-page app that just shows a text or something like that. We still have quite a few challenges to get through, but I do anticipate many improvements in the coming year as we continue to collaborate with other folks on various platforms and various key components that the whole community will use. And then I'll leave you with our blog here, which I've recently, at the beginning of this year, made a couple of posts to kind of lay out the status and what we did in the past year. So I'd like to acknowledge the help that we had from many different folks here, the MakePad team on the left, Robius folks working in the middle, and then on the right, several folks that have contributed to Rubrics. And with that, I will take any questions. Thank you. And sorry I ran out of time. I wanted to show some other cool code examples, but it is what it is.
Well, yeah, so I think it was a fantastic presentation.
Thanks.
We're gone slightly over, so we still have time for 2 or 3 questions. So if you have a question, could you please come to the front of the room? Have we? I see someone's getting bullied into asking a question up there.
I have a question.
Yep.
You showed an example where you did a query for one of the things in a view, one of the buttons. It used a macro, and I was wondering, is it like statically checking that button actually exists?
No, it's not static. So that's actually one of the, I think, points of consternation I've had about using this framework. One thing that we have is recently we added a strict mode, right, which will warn you if you have, queried a DSL item, like if I accidentally wrote like, delete or something, right? That's quite hard to check, to identify. So, let's say I wrote delete instead of delete button, right? Yeah, here. So if I did something like that, yes, it would silently do nothing by default, and that's sort of, not ideal when you're testing. So we have a strict mode that will warn you if you've made like a DSL typo, but the right way to address this, of course, is with an LSP of some sort that would integrate and, maybe check some of your DSL names at compile time or before.
Thank you.
I have a question from the YouTube chat.
Okay, hi YouTube.
What is the state of animation for MakePad and Robius?
Oh, sure, yeah. I mean, we have lots of different animations. I don't actually use too many of them in Rubrics, but one example is here. If I can find my own message, let me clear out some of these so you can see better. I can, a very simple one would be the editing pane, which is not fully finished, but you can see I'm able to slide stuff up and move things over. Another example would be the profile thing here, right? So you can animate things in and out like that. We have a variety of other examples in the MakePad, like the more visually impressive MakePad apps that, this is a chat client, so there's not a lot of that. But yes, absolutely. We have, arbitrary support for animations in a variety of different, decay models and timing models and things like that.
Okay, if we have no more questions. Oh. One more.
Is there any plan to support accessibility?
Yeah, yes. So I'm not able to show off any of that today. We as a community have kind of rallied around AccessKit, a great piece of work by Matt Campbell. Yeah, okay. So we will eventually add support for that into MakePad itself. I'm not really an expert UI developer, despite maybe what you've seen today. I'm really not the right person to do this stuff, but the idea is to emit a UI tree, much like the widget tree that you saw earlier, that can be then connected to AccessKit in order to have that connect to the rest of the platform-specific accessibility APIs.
Amazing, thanks.
Yeah, but I will say it's probably going to be a while, unless, of course, I can have undue influence on the MakePad team to prioritize that, which I will try.
Thank you very much for everybody who came to the talk, and thank you, Kevin, for the fantastic.
Thanks for listening. Appreciate it.
You covered a lot of ground.
Yeah, too fast. Hey Bart, how's it going? Oh, sorry. How do I shut this off?
I'm really excited to see you getting closer to the sort of.
Oh, cool.
Oh, hey.
Yeah.
Hold on, let me take this off so everyone doesn't hear our whole conversation.
Okay, that's fine. So let me pop this open and get it going real fast.
That was a lot of stuff that I didn't know about.
I'm showing like 5 minutes still. Do you want anything earlier?
I don't think. Well, maybe 10 and 15.
Okay,
Good way to
I'll do 15 and 10.
like to show some more code and show how we actually do it.
Don't be afraid, I think, to stand up and yell.
Well, like, I mean, you have like 5 minutes of leeway to cut
me
into
too.
your...
Yeah, I understand, but we just want to.
If we give time between the presentation schedules that you can also cut into. Because in my opinion, it's quite long.
Let people set up, so we can still ask like people can still ask questions, but we want
exactly.
the next person.
And I should have been up here setting up this faster, but I didn't know they wanted my laptop right away.
Your presentation is 10 minutes, and then after that there's 5 minutes for questions, which you can cut into a little bit if you want. Wait, do we have questions for this or not?
No, we don't. The GOSIM talks do not.
No, wait, these ones. But these are 15 minutes then, I think.
These are both 15 minutes. We don't have. We have Q&A after both of them. Because then
so it's 15, 15, and 5. But that's weird because then you have Q&A for 2 talks at the same time. How is that scheduled? How long did you plan your talk to be? Let's say that. If you plan it for 10 minutes, then you have 5 minutes of questions. Okay, that's excellent.
I think.
Feel free to cut into the question slot a bit if it helps your talk.
Do you guys need more water?
Maybe you can refill one of these. I think we have a sufficient amount of glasses.
Yes, glass are okay?
Yeah.
Yes, I will.
Okay, I need a HDMI cable and a...
It should all be down here, I think.
Okay, there it is. Oh, perfect. That's all I should need, I think. I don't think anybody has sound. And so we should be good to go. Let me go to where the slides are. Which slides do I want? Oh, I don't see.
It's mantra.
It's mantra.
Wait, no.
Here's the slides I have. I don't know that any of these are here. These are the slides that I was handed.
These are by Manuel's here.
Yeah, Manuel Halt should be the PDF. I don't think it's here. I'll go find him.
Who's supposed to go first? Should we reorder it? Or
If you have your laptop scale, it's might be easier.
Manuel first, and then Jalong. Why don't we start Jalong while we...
We also have a USB stick if you just want to transfer the slides, whatever you like.
So, we're getting set up here. Okay, is it working now? Oh, perfect. Actually, even better. So what we're doing now is returning to the GOSIM Spotlight Talks. I talked about this a little in the morning, but for those of you who may have missed it, this is a special program run by the GOSIM organization and that brought some speakers through community nominations to here to present work that's new and innovative and that many people in the Rust community may not be aware of. So that's the focus. We had a huge number of great proposals, and we had to make some very hard choices, and we ended up with some amazing work. So the first person we have is Manuel Hetzel, who's talking about. Did I get your name right? I'm sorry if I pronounced it wrong. Who's talking about requirements traceability in Rust. And this is a talk that I'm especially excited about as somebody who's taught some software engineering. It's a topic you don't hear much about in the world these days, but it's absolutely critical to a lot of buildings. So I'm really excited to have your talk. Thank you very much.
Okay. I think the microphone works. Slides. Yeah, perfect. Okay, so hello. Thanks for attending my talk about my project Mantra. It's an open source tooling for requirements traceability. Mantra is short for either managed tracing or Manuels Anforderungstracing. And for those of you who don't know German, Anforderung is the German word for requirements. You may choose either one, but the managed tracing is more enterprisey and Manuels Anforderungstracing more personal to myself because, yeah, as mentioned, my name is Manuel Hatzel. I'm from Salzburg, Austria, and since May I'm working as a tooling engineer at Ferris Systems. In this talk I try to go through first with a quick what and why of requirements traceability, get you up on speed. Then usage flow, kind of top down of Mantra, first defining requirements, tracing those requirements to code, linking test coverage and reviews of those requirements, and then collecting everything together and generate a nice traceability report. Okay, so let's start with requirements traceability. What is requirements traceability? Nice IEEE definition we don't have time for. Traces are those dotted dashed lines between requirements, and artifacts, they representing kind of relations between them. Artifacts could be code, models, diagrams, whatever. And knowing and documenting those traces, that's kind of requirements traceability. I hope that's okay with you. Why I think about requirements traceability? Well, it's mandated or recommended by many safety critical standards, for example, ISO 26262 automotive, DO 178C aerospace. It can also help to automatically track project progress and status, which I quite like. And then it can also help to with change management, compliance verification, and software comprehension. Why did I create Mantra? Well, I wanted to keep better track of my own projects without much manual effort. And then for external people or myself a few months in a project, I wanted to better understand the project structure to faster get to a point where I need to go to fix bugs or implement new features. Then when starting out with Mantra, I couldn't find any open source alternatives that was able to trace Rust code and is built in Rust. And then lastly, because Mantra was part of my master thesis I did in collaboration with Infineon, and they wanted a tool that integrates well with their embedded Rust code and helps them with ASPICE certification. Okay, so now let's see how Mantra works by starting to define requirements. There are at the moment two options. The simple one is on the left side, kind of markdown wiki, I call it. You define your requirements in one or more markdown files. This one is quite nice because you can define your requirements and then put it like in a GitHub wiki, so you have it directly next to your open source project. The alternative to define your requirements in following a JSON schema, this one is usable for exchanging requirements with other requirements traceability tools. The most important part here is those bold text. That's our requirement IDs, and those are used to uniquely identify requirements. You may also see that IDs can also be used to represent and visualize a kind of parent-child relationship between requirements. So my ID.subID at the bottom is the sub-requirement of my ID. That's basic stuff at the moment. For tracing to code, Mantra's focus at the moment is to handle traces between requirements and code. So let's see how we can trace to code. You could also specify or add traces via JSON file, but I myself find it easier during development to manually add traces directly to the code following some Mantra pattern or tracing pattern. And for Rust code, I have three variants. At the top, you see an attribute macro rec. on the struct foo. Then on the bar field, you see a kind of an angle bracket pattern that's similar to the attribute macro. And then at the bottom in the foo function body, the recconf function macro. You can have the same name for rec and recconf because macros. To collect or to detect those traces in code, I use tree-sitter. So I pass a Rust code file by file and then walk through the generated AST to detect those traces. This means it's language specific for this approach, and I refer to it as the AST-based one. The nice benefit of the AST approach is because we can now link traces to whole code blocks, and this is quite useful later when talking about test and coverage, linking everything together. As you can see in this example, rec2 is for the whole definition of the struct and also for the function body completely just with one trace. Because it's language dependent, only currently Rust is supported. For any other language, and a text-based file basically, you can define the angle bracket pattern, and then I will search for it line by line via regex. This allows to, at the moment, basically trace in any programming language, and also configuration files, which is quite useful, for example, to add your requirement traces in CI/CD workflows to ensure tests are ran before your releases or so on. Talking about tests, let's see how test coverage and reviews are all linked to requirements. For this, I take again this Rust code sample before with the foo function, and now we assume that we have this test foo function, test foo1 test that is testing our foo function, and foo is traced to the requirement rec2, and we can now explicitly add the trace above this test function to like say that this test is testing this requirement and also this foo function. And now once we run and execute this test and collect statement coverage, we can like link the covered lines to the requirements that are traced to those lines, and this gives us collecting everything together like a confidence that requirements are actually covered by tests. Going one step further, we could now even decide whether we want to remove this trace, this explicit trace on the test function, and because if the test is still running the foo function, then the requirement will still be covered. Or we want to keep the trace on the tests and then get the higher confidence to our tests that the tests are actually still executing or passing implementation code that's also linked to the traces. So kind of changing between. Then there are always requirements you cannot test or you cannot trace to one code section. So or you want to additionally add like manual verification steps besides testing or automated testing. And this one with Mantra you can define like your requirements in text files. And this combined with testing then makes requirements either covered by tests or manually verified or both. Okay, so now we have everything set together. Let's collect this and then we can generate the traceability report. For collecting, you run the command mantra collect in your terminal. This will look for a mantra.toml file in your current working directory or the current working current directory, and then this will store everything in a mantra.db SQLite file. SQLite because SQL is nice to query lots of data, and you can store it in your project repository. Okay, so we have collected everything, and now to generate the report, you run mantra report in your terminal. You can choose at the moment between JSON and HTML. And as you can see on the image, this one is like a sample report of my pacemaker demo. It's available on mhutzel/pacemaker. It's like demoing of an embedded device to get traceability with Mantra. For the reports, the JSON one has a fixed schema to help with interop with other tools. For HTML, I use a Terra templating engine, which makes it quite nice to generate custom HTML reports, but I also provide a default template if you don't want to create your own template. Okay, that's it from Mantra so far. In the near future, okay, time is okay. I want to add being able to like set multiple parents for one requirement in the Markdown approach, because for JSON it's already kind of working, but circular dependencies are a bit nasty at the moment. And JUnit and Kubertura having as test and coverage input would also be really nice, because they're more like standard, but this requires some database schema changes in the background. I'm currently looking into this one. Another requested feature was to be able to override test and coverage data in reviews in addition to just verify requirements, basically. To improve change detection, I also want to add hash information of requirements traces, reviews, and so on, but I'm still not sure what data should go into calculating those hashes at the moment. Then for C and Python, I also want to get AST-based tracing, because those languages are quite often used in safety-critical applications. Yeah, so having those with the AST-based one is quite okay, or quite important. Then for the long term, I would also like to have like integrated checks directly in Mantra and tailored reports for safety-critical standards, so to help and reduce manual effort for certifications. Custom checks, being able to run custom checks in CLI would also be nice, so you don't have to write your own application just to query the data from the database. And then condition coverage in MCDC, again, something that's relevant for safety critical. Having MCDC information inside Mantra would be quite useful for the reports, but not sure yet how to store MCDC coverage, because Rust and MCDC is still a work in progress, so I don't know how this data will look. And then for the IDE extensions, I would really like to have like auto-completion of the IDs, or a documentation of requirements on hover over the traces. So if you, some of you has IDE and editor experience, please get in contact with me. And then, yeah, there are so many programming languages. I can't implement AST-based tracing all by myself. I tried to like generalize some crates to help with trace collection, but yeah, it's just takes time to integrate everything into Mantra. With that, that's it with my presentation. Thank you.
Thank you very much. That was fantastic. We're not doing Q&A for the GOSIM talks for the very good reason that afterwards and throughout the week, up on the mezzanine above the eating space, there's a whole GOSIM area where Manuel and other people will be up there to answer your questions and talk with you about what they're doing. I would really encourage you to come by and chat with them. So that's fantastic. So our next GOSIM speaker is Xiaolong Fu, who describes himself as a country boy from eastern China new to Rust, which is, I think, a cool description. But what's even cooler is the work that they're doing, which is about a new but also old approach to async programming.
Do you have your own laptop, or do you have?
I got one laptop, but
Async's a complicated topic, and I think the stuff that Xiaolong's doing is kind of cool. So I'm really, really excited about that. It may take us a minute or two to set up, I guess. Beg pardon? Okay, that's fine. Yeah, let us get. It'll take us a second or two to set up. So if you need to take a quick break, now's the time. But we should be going here in a minute or two. Oh, you got my power. It's on the left.
Oh, it's not the normal one.
Yeah, so just USB-C port. I don't know if it's here.
Anything I sent in was here.
This was exactly. So
this is not one of yours, right?
Did you send in a talk? Did you send slides?
I sent a PowerPoint.
Huh.
If you didn't, easiest for now is to get your own laptop and start that up, because it's not in this directory apparently.
Yeah, this is what was on the USB key that I got.
We got a USB stick with all the things that were sent in. So
yeah.
It's not in there, then it's not in there.
I don't know. It said it didn't file system check, so it may just be that it's broken.
Yeah.
So.
Yeah, it's fine, I think.
Yeah, if we can get yours going, that's better.
Do you have an HDMI port or not?
Yeah.
Wow, in the back. That's cool. I've never seen that before.
USB-C power.
Does that work for power? You'll be all right for you'll be all right for 10 minutes. Don't worry about power. All right. So you're not seeing video yet?
No, it's still starting up. Still, give it some time. Ahead of schedule anyway, so it's all fine, don't worry.
Sure thought it didn't chaos.
We are ahead of schedule anyway, it's all fine. He's only supposed to start in 2 minutes. So, and then we have 5 minutes of margin to play with.
Yeah. We'll be all right. I don't think so. I think it's fine. I don't think there's any problem.
Nah.
I think it's fine.
I think it'll be fine indeed. Just let them relax for a few minutes,
Yeah.
check their phones.
Yeah, exactly. Well, I just thought we might have something useful to say, but
Is it good?
There we go.
Do you want a clicker?
And
you can put
tapping.
okay.
Or whatever you
That's
like.
fine.
Good.
All right, thank you very much. We're ready to go. So let's welcome the speaker and yeah.
Hello everyone. Today I'm going to share the story of Deras with you. And first I will introduce the key features of Deras, and next I will share the core concepts of Deras and the use cases and the performance of Deras, and last I will introduce my team. Okay. Deras is an easy-to-use, high-performance framework that follows the concept of flow-based programming. It's designed to simplify the development of complex asynchronous applications by providing convenient programming interfaces and the robust task management capabilities. And our site is deras.com, and you will find documents and logs over there. Next, core concepts of Deras, that is flow-based programming. Flow-based programming is proposed by J. Paul Morrison from Canada. He came up with this idea while working at IBM. And when he was simulating the traffic flow at a gas station in Montreal, he thought that what if we regard data flow as traffic flow and make the working nodes work together like the gas station? This inspiration was finally implemented for the first time in the system of the Bank of Canada and created a software legend that has been continuously running for over half a century. And a study published by ACM in 2004 proves that FBP can shorten the software development cycle. Flow-based programming proposed by Morrison effectively reconstructed the early program control method, allowing data to be passed between different applications in the form of streams, allowing programmers to write functions that perform specific actions and then use the network to define the relationship between functions, so that we can execute these functions concurrently and pass data between these applications. And Planck, one of the important founders of quantum mechanics, of course he is not a user of Rust, but he once said a truth about scientific truth. A new scientific truth doesn't triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up and that is familiar with it. Nearly half a century has passed since Morrison first discovered FBP, and programmers who worked in the early days of the von Neumann era are gradually dying out. And instead, a new generation of programmers who are frustrated by the shortcomings of the traditional paradigm are gradually growing up and are willing to try new things. Of course, I am one of them. Flow-based programming treats the program as a black box network and achieves communication between different work nodes through predefined packets, flowing asynchronously in channels with limited capacity. FBP is actually a special case of data flow programming. The common modes supported by flow-based programming includes merge or compare, split or duplicate, sorting, and subroutine, and other patterns. Next, I will display some use cases and the performance of Deras. Deras is currently used by Olocom, a company from Germany that designs automated safety systems. The system enables automatic collision avoidance for material handling equipment and enhancing operational safety and efficiency. For further details, you can refer to their YouTube account or their website. And next, we evaluate the performance of Deras by running benchmarks on the RustStream bench. RustStream bench is a benchmark suite that focuses on streaming applications run on multi-core environment. And it contains 4 different benchmarks. The first one is microbench that doing some mathematical computation. And the second one, bzip2, it simply compresses and decompresses some files. And image processing processes a group of images with 5 different filters. And the last one, eye detector. It detects the eyes in the face with an input video. Oh, sorry. And this is the experimental results. When I was preparing the PowerPoint of this page, my mentor came in and asked me, "Oh, looks like the stock market doesn't go well," and I answered him, "This is our experimental results, of course." Yeah. So anyway, the experimental results demonstrate that as parallelism increases and the workload scale, Deras progressively narrows the performance gap with other frameworks and even outperforms some of them in specific scenarios. Notably, our evaluation accounts for the time required to construct Deras' workflow graph. It is a critical factor that often overlooked in runtime comparisons. These findings suggest that Deras achieves competitive efficiency in parallel task execution while maintaining flexibility in workflow construction. And last, Deras team. These are the main members of the Deras team. Mr. Ma is the owner of Deras project, and he is guiding me to complete this job. Yeah. And Mr. Feng is my mentor, and he is also very interested in the progress of Deras. And I'm Xiaolong, a second-year master student. And Xue is my junior, and he has also made important contributions to the Deras project. Here we welcome everyone to express your opinions on Deras, and you can also join us to improve the performance of Deras and design new features for it. That's all my presentation. Thank you.
So the way the schedule's worked out, we do have a little bit of a break at this point. People can get up and move around if they want to. And starting at 3:30, we have Arya talking about how something. I don't have notes here. Excellent. Distributing binaries to millions of machines. That sounds kind of awesome, honestly. So yeah, we will do that here in just a little bit. Do go to the Rust Spotlight booth up on the area up on the mezzanine and check out what some of these people are doing. It's really, really fun to talk to them about.
Sorry. Yes. Thank you.
and they have been quite basically the science to just maintain the technical voices, to just maintain and quite out for the this year. So that's why there's so many after this year. I just noticed we don't actually have enough
Yes, absolutely. So, unfortunately, we're really kind of at the limit of this room a lot. So if you have an empty seat next to you, please stick up your hand and wave it so that people who are looking for a seat can find one. We really can't have people sitting on the main stairs because the fire people get justifiably concerned. I'm sorry about that. So please too try to make room for everybody. I want everybody who can to see it. The other thing that everybody should know is that we are both live streaming and recording these talks, so you know, people who can't make it in will have a chance to see it, but hopefully everybody will be able to make it. With that, I think we're about ready to go here. I think we're going to go ahead. We don't have any more people coming. We don't have any more seats anyway, so yeah. So welcome back to the ecosystem track. I have the great privilege now of introducing Arya Desires, who you may know online as Gonkra, who is the author of The Rustonomicon, one of my very favorite Rust books, Learn Rust with Entirely Too Many Linked Lists, Cargo Dist, and Cargo Mommy. And, you know, I've admired Arya's writing from day one, and I really feel privileged to introduce this talk. Arya is now at Astral working on Python bindings and is going to talk about what it says up there on the slide, shipping UV's binaries to millions of machines. So thank you very much. Let's give a round of applause.
Hello. Okay, so let's talk about what goes into shipping UV's binaries to millions of machines. First off, I should explain what UV is to you if you haven't heard of it. UV is a fast all-in-one Python interpreter. For Python people, this means it can install your Python runtime, it can create virtual environments for you, it can resolve dependencies, install those dependencies, build packages, a bunch of other stuff. For those who know Python tooling, this means it is a drop-in alternative to pip, pipex, pym, virtualenv, poetry, tons of other tools, growing every day. And the vision here is simply just, it's awesome that all of these great tools exist. It's really frustrating that it's multiple tools and you need to know about these tools and you need to know how to put them together. It'd be really great if there's just one tool that you get and it does all of the things and it all works together because it was all built together. As a bonus, it's also like orders of magnitude faster than a lot of these tools because they are quite understandably and reasonably written in Python, and UV is pure Rust, which is why I'm giving this talk. For Rust developers, here's the simple answer. It's just Cargo and Rust Up for Python developers because we love Cargo and Rust Up. It's a great experience, and we want Python developers to have that experience too. In terms of how successful this has been, a lot of people interested in our repository, a lot of people contributing to our repository. A catastrophic number of people are downloading this every month. 42 million downloads a month. Terrifying number when I heard that. And honestly, an enormous percentage of the Python market share. So PyPI is Python's Crazy.io equivalent. The number I've been quoted, which sounds fake to me, is PyPI gets 2 billion package downloads a day. And that means UV is used to download about 400 million Python packages a day based on this PyPI market share. So needless to say, UV is a lot of companies' critical infrastructure. It is their Python tool. And since it is their Python tool that installs all of their Python stuff, how do they install it? That's the talk. How do those 42 million downloads every month happen? So let's figure this out. As I said, UV is a pure Rust project. We're all Rust developers here, so we know the best way to install a Rust project. Obviously, you just cargo install it, right? And actually, this does work, although we're not on Crazy.io. You have to pass --git, but that's fine. But there's one kind of big problem. We're for Python users, not Rust users. And so saying like, oh yeah, just install the Rust toolchain and then you can install your Python toolchain, not really the vibe. Also, it would be really slow. But okay, they're Python developers. How about you pip install UV? And actually, this does work. And my understanding is this is quite popular. We'll be talking a bit about how we accomplish this later. But there's still another problem here. We're how you install Python. You can UV install pip. This can't be the be-all, end-all. It's great for people migrating to UV, but we want people to start at UV and be able for that to work. So we need to solve the bootstrapping problem. And we need to make something from nothing. And by that, I mean, we want our users to basically know nothing. They could be, this UV could be how they start programming. So being like, oh, you're a programmer already is unacceptable. Also, like, I'm a programmer and I still really want a simple installation process. We also want to assume the computer has basically nothing installed because we just want to run on every machine we can. And as kind of a bonus constraint here, we really want low latency between us releasing and you being able to install. Because we're always making new features, we're always shipping fixes, and we want our users to get those immediately. So something like, oh, just wait for a distro to package it is not really a good solution for us. It's a good like secondary solution, but we want to have an answer for all of our users can get the new updates right away. None of these constraints are novel. This is the exact problem RustUp has. And I'm sure a lot of you are quite familiar with the solution RustUp has. It's everybody's favorite, the curl sh script. So in terms of the constraints from the previous slide, how much does a user need to know? They need to know how to launch a shell and paste a command into it. That is genuinely a non-trivial requirement, but for a CLI tool, it's not an absurd requirement. They're gonna have to learn how to open that terminal real quick. So that's good enough. In terms of what needs to be installed on the computer, you need to have something called curl and something called sh. And I have feelings about these things, but it's pretty good. And in terms of the latency, these kinds of scripts, all they do is do some platform detection and fetch a pre-built binary from the developer's infrastructure. So the latency is like as low as it can be. As soon as the release happens, it should be available. So that's great. This is a really solid solution. People have beef with this solution, but it keeps happening because it's real good at its job. So of course, in UV, our installation page, it has a curl sh expression. It's the first thing we recommend. And ours is actually based on the RustUp one. So our installer is generated, our shell installer is generated with a project called Cargo Dist, which I worked on. And Cargo Dist is basically a fork of RustUp's install process to try and make it more generic so more projects can use it. Here, another project used it, cool. But immediately we can already see some beef with curl. Not every machine has it installed. So we opted to have some extra instructions for, hey, if you don't have curl, use wget. RustUp decided not to put that, you know, whatever. Again, we're trying to be like, we don't want to assume you know anything about anything. I had to cut a lot of slides from this talk because it's so short, but here's one part that I refuse to cut. So as I mentioned, RustUp init.sh, it has to figure out like what platform you're on, what artifact to download. So we get to the point of, okay, cool, I know the URL I want to download, I just need to call curl. Here's all the code to call curl in RustUp init. It's not trivial. Everything is really complicated with these scripts because you are truly assuming nothing about the machine. There's some stuff in here like it calls curl -- help and parses the output to figure out features your curl has. Like, it's rough. I also have beef with sh, of course. If it ever comes across that I despise shell scripting, it's because all the shell scripting I've ever really worked on is these curl sh scripts, and it is the worst shell scripting you can ever do. Bash is fancy. Bash is the future. I have never even heard of fish or new shell, absolutely fanciful notions. We are trying to run on any machine we can, so we need to work against some like common ideal POSIX shell, like perfect thing. you say I want to run in bin sh, and this is just like an alias to like some shell your system has, and you just try and write against a subset that should work in all of them. And rest up init, there's this attribute. There's these attributes for shell check. Shell check is a linter for shell scripts. It is a godsend for this, and you can basically say, hey, please make sure my shell script should work in dash. Dash is an intentionally very bad shell so that they can make it run fast. And that makes it a really good target for this kind of work because it has like basically no features. It's practically an exact POSIX shell. You see the one big exception here is, can we have local variables? Yeah, like the base POSIX shell just didn't specify that, I guess. And writing non-trivial things without locals is awful. But that's fine. Like this is a super standard extension. Everything has it, except for Corn Shell 93. Which apparently some systems are still running, and rest up init handles that for you. Again, this talk could have been hours of this. This is my favorite script. There's so much great engineering that went into it. This stuff is hilarious, but the engineering work is real and great. Also another problem, Windows doesn't have sh. So this solution doesn't work. So the REST up website, it will just detect, hey, you're on Windows. Here's just download the binary and run it. This isn't too bad because there's a bajillion Unixes that are all weird, and there's one Windows, and it runs on 3 platforms. One of them is dead, and one of them is a meme. So really, there's like one Windows platform you ever need to care about. Cool, great. This isn't too big of a deal. However, UV did diverge a bit here. As I mentioned, it uses a tool called cargo dist, and we're trying to make things more uniform. So having this kind of like bespoke executable solution for just a few platforms wasn't really as like I can just toss this at a random program. So we built an ermx script, you know, ermx, which is the Windows equivalent of curl sh. And it has other fun stuff in it, like the curl script. Again, it's a bit easier because there's just one Windows. There's more than one shell. One of them is a toxic lesbian that I don't want to talk about. I actually do really want to talk about it, but I can't talk about it in this talk. So that's how we get our binaries. How do we actually build our binaries? So first off, our platform support, it's a pretty normal looking matrix. We've got Windows, Linux, Mac OS. We've got x86, ARM, and whatever IBM wants. IBM's always up to something. So, you know, it results in a lot of platforms. We have to, you know, we're going to have to solve some interesting problems here, but nothing too exotic. Again, we're all Rust developers. We know building Rust code is really easy, so I'm sure this part's really easy. And it is, so the problem is Rust is really good at building your code reliably into a binary that will run on the current machine. Once you copy that binary to another machine, hard to say if it'll work. Rust isn't as great as helping you do that part. So a few problems you'll run into, system libraries. The most infamous one here that literally everyone runs into is OpenSSL. As soon as you include hyper or request in your project to do any basic HTTP, you will end up depending on OpenSSL on Linux. And there's a feature flag to say, hey, don't use OpenSSL, use RustTLS instead, that everyone who ships binaries sets to fix this problem. So, you know, PSA, use the RustTLS feature flag in request or hyper or whatever. Cross-compiling, it's a problem. There's a few really nice cross-compiles, and all of them are really hard. There's also SDK and libc versions. So like, oh, I want to run on like glibc 2.8, or I want to run on macOS 10.14 and later. Rust doesn't really give you great tools for doing this. It kind of just looks at what your current system is and goes, I'll build against that. So if you build on a really old machine, that'll work, but otherwise there isn't a way to ask for it. And there's just a long tail of like quality of life things like Windows manifests, macOS bundles. That'd be nice if Cargo helped with, but it doesn't. So you kind of fall off a cliff as soon as you start caring about that stuff. So in terms of cross-compiling, the tool we use is Maturin. Probably a lot of you haven't heard of this. It's part of the Pyoxide project, so it's part of this project for building binaries for Python packages. But it's just kind of a general purpose Rust cross-compiling tool. And all Maturin is the insight that, hey, Rust is really good at doing these host builds. We definitely know it can do host builds really good, building for the exact machine that we're on. Let's just turn all of these hard cross compiles into host ones. And we can do that by just throwing enough Docker and QEMU, just emulate until it works. A lot of people are very indignant about this or insist like, no, there's got to be like a good way to do it or like a right way to do it. And it's like, no, this is just like great. Like cross-compiled tool chains are hard. It's not even strictly Rust's problem. Like anytime you get some C or C++ code involved in your build, it's going to become a problem. Why not just have a Docker image, maybe with some QEMU wrappers that just has all of it set up for you? People have asked me before, like, oh, I'm trying to pass like Target to do some cross-compile stuff. And I'm like, why? just use the Docker images. And honestly, this really does work. It solves cross-compiling and libc versions. There's a bit of an issue with if you want to target really old OS versions, these Docker images are essentially on really old OSs. And if you get really old, eventually your compiler stops working because it requires a newer version of the OS. So, you know, there's fancier things like the crimes Zig does to make this work. Bless you, Zig, you're doing wonderful crimes. But those come with caveats. So again, really solid solution. Just use emulation. Also want to give a shout out to the Python community's many Linux standards. So for a long time, they have been bundling pre-built binaries into Python packages. I think NumPy is a famous one. It's got like Fortran in it. No one knows how to build Fortran. So like you got to ship some pre-built binaries for that. And you know, they kind of wanted a notion of like, okay, if I build a Python package that I claim works on Linux, what should I assume and support for everyone to agree I've done a decent job of trying to support Linux? Because Linux is a mess, and like Nix doesn't count. So they have these standards like many Linux 2010, 2014. Eventually they were like, we should stop using dates and start using glibc versions so you actually know what you're targeting. These are absolutely great. And most importantly, they provide Docker images. So Maturin can just grab those Docker images and use them as the basis for these cross-compile environments, which is great. Python has great things. Also, shout outs to Pyoxide. This is, again, part of the same project as Maturin. This is the actual thing that goes, hey, cool, I have a Rust package. I've built some binaries for it. Please package that up into a Python package that embeds those binaries so we don't fetch them. They're like actually embedded, I believe. And they're good to go. You can just publish those straight to PyPI, and Python has some fancy system for specifying like these things called wheels and like what platforms they support. So all of the like detect what platform you are on and which pre-built binary to use is kind of just like a pre-built thing into Python itself, which is great. Also, finally, look, sometimes you can use silly solutions and they work fine. I mentioned that RustUp had kind of this bespoke one-off solution for like, Windows is a mess. We'll just show them the binaries on Windows. There's this problem that Python, like a lot of things like Python and JavaScript need to solve, where it's like, I've made an application in Python or JavaScript, and it's like a script that you can't run as an, like, it's not a binary, it needs to be fed into an interpreter. So on Unix, you might like generate a shell script that claims to be that binary, and all it does is like run your interpreter with your actual script. This doesn't work on Windows because like .exes are like actually magical and special in Windows. So rather than generating a shell script, we'll just pre-build some executables, and we include bytes these straight into UV's binary. So if ever we're like, oh, we really need We really need a trampoline right now. We just spit it out onto the disk. These have been checked into Git for 3 months. Someone just builds them on their machine and checks them into Git. It works. You know, whatever solution works. That is everything. That's how we get binaries to millions of machines. We have like a minute. Anyone?
Absolutely fantastic. Do we have time for questions at this point?
Literally a minute.
Oh, okay, we have 2 minutes left. So we can take like one question. Who has the most important question?
No pressure.
Yeah, no pressure. All right, we still got somebody with their hand up here in the front, so I guess come on up and ask the most important question.
Hi, it's the only question, I guess it's the most important one by definition. I was wondering, you said if you chemo hard enough, everything becomes a host, but if I need my host to be Mac OS or Windows, and I don't happen to have bought those OSs, what do I do?
So I'm going to be honest, I don't know the full details of the Docker images. If the QEMU stuff doesn't work, then you just get a Mac OS or a Windows runner. Like there's, I kind of skipped over the fact that Maturin provides a GitHub action for this. So it figures out how to allocate a machine. But specifically, it doesn't require like paid runners or anything. So the Mac OS, Windows, and Linux ones are enough to cover everything.
Okay, cool, makes sense, thanks.
Very cool. A couple of quick announcements before the break here. First of all, if you want to experience mixed reality Rust programming or play around in Mortal Kombat, I guess those are things that go together, go see the MakePad area in the second floor of the reception room. The MakePad room is going to be cool, so I would highly recommend that. The second thing I was asked to announce is that there's going to be a second podcast recorded this evening, and it's an accessibility-themed one. I don't quite understand what all that means, but there will be these 2 podcasts, and you should be aware of them and ready to go. With that, I think we're ready for the break. We will come back at 4:20. So I will see some of you back then. Thank you very much once again. Great talk. That was fun.
a second. I used to have a Mac. Is it down or is it?
It might be on I think I know where it might be. Hold on. So I guess down the settings.
No worries, man. No worries. That's good.
Display. Arrange.
Oh, that is. Yep. That's
Go
awesome.
through it, and let's take this and move it out.
Ah,
All right.
beautiful. Beautiful.
Okay, and can we make this full screen? Yes, we
Yeah,
can.
go on. Yeah.
That's the boss I got.
Very cool. Slides are great.
Thank you.
Okay.
And now we're all good to go.
I think we should be good Ruby. Do we have to test the other laptop? Should we test the other laptop? Someone else is speaking after us?
Should we quickly test the other one, or
we'll deal with it.
That's fine. We're getting you it tight now. So. Also, I think they're a MacBook as well, so whatever works for you will probably work for them.
You'll have to stay and act as an advisor.
That would be fantastic.
So my name is Lucas View. Mine is Parsons.
Barsky. David Barsky. Okay. I will try not to butcher that.
Yeah, I think you already got it. As long as it's not
Okay.
Any relation to Niklas yet?
Unfortunately not.
Our next speaker is just not there yet. I think he will join later.
Does it make you? No, it's just up to you. Because he might be nervous. I don't know. I don't mind standing in the back.
All right.
Are you ready?
Yeah, I'm ready when you guys are. Yeah.
All right.
Hello.
I'm going to take this water.
Hey everybody, are you ready? Okay, we're coming on to the home stretch of the day now. But before I kick off these talks, I'd just like to give a thank you and get a round of applause for two of our other sponsors, ARM and Infineon. Thanks to our sponsors, they with the funding and the support that they provide, it makes days like these possible, and people get to attend, and we can have such a big, fancy event as we're having right now.
Keep it spotlight. Oh, here. Sorry.
Just in the spotlight.
Oh,
This is-
my bad. Okay, cool. Oh, hello.
And here in the spotlight right now, we have David Barsky and Lucas Vert. David helps to maintain the tracing library and Rust Analyzer, and Lucas is a lead of the Rust Analyzer team. Yep. And they're going to be speaking about the magical world of Rust Analyzer today. So I'm looking forward to that.
Thank you all for having us. So when we pitched this talk initially to Mara, as we said, like, you know, it'd be kind of cool to talk about how Rust Analyzer pulled off this really big migration of like effectively 30,000 lines of code. And it turns out the answer to that is actually kind of simple. It's like one macro, just write a macro. It's fine. So we kind of lied a little bit tomorrow, and it was a little too late to update the website. So it's actually more this, where like we're more interested in talking about like, so it has this like super sophisticated, interesting incremental computation library and why you may want to use it. We'll also cover why you may not want to use it, but we'll just sort of build up to it and hopefully give you an intuition as to why you care about this, why you might be interested in this, and maybe sort of judge for yourself whether or not it is a good idea or not to use it in your own projects. So let's start with a kind of a simple story or a common story about performance optimizations, right? You get a new requirement from somebody, maybe you foisted it on yourself, but you want to figure out how many structs do I have in my project. We have a few requirements on this. The first of which is you have to count all the crates, all the structs in your crates, as well as all your dependencies.
it has to be fast, then ideally it should be correct. So let's say in this array, it's basically somewhat compiler shaped, right? And you want to put in a report. It could be like you could be counting things, but it doesn't really matter. You just want to find out how many structs there are in there. So I asked Claude 3.7 to write me Python because I do not know how to write Python. So it's like, just give me all the structs in a folder, which it says in a file, but who can say? It's AI, whatever. But basically, we read it. We look for like the bytes, the string bytes. It's probably not correct. You could probably find a few issues in it, but this is our first pass at a parser. So let's say, maybe it mostly works, but it's not fast enough. And so we break out the really common. We go to the next step, which is to say we rewrite it in Rust. I've done that multiple times in my career. I've literally moved Python to Rust, and it works better than you'd expect. Maybe you expect it, but anyways. So let's look at like the Rust code actually. And in this case, this is a bit more rusty. There's some code that is not fully yet stable syntax, but it just sort of communicates the ideas a bit more elegantly. In that first, we have a struct called struct def, which has an ident, and there's a whole bunch of other fields that says like, that might have the derives, that might have the methods, all the other stuff. That's what the small little comment there implies. We first then look through all like the structs in a project. We'd return an iterator and for each, and then we go through for every single crate inside of the project. We just sort of look through it, and for every module inside the crate, we just find all the structs, and if we see it's a specific definition inside a module is a struct, we return that definition. That's really not complicated. This is kind of simple Rust code. Looks reasonable to me. But what if that's not fast enough, right? So that's annoying, but let's maybe add some parallelism, which is, the common thing. And, Rayon is great. And again, this is simplified pseudocode that's not real yet, but like, we put in a sprinkling of like this par iter. And all of a sudden we have like per crate parallelism, which is actually, fun fact, what we do in Rust Analyzer today. If you use Rust Analyzer and when you open your project, you might see a small little bit of a small little item that says indexing in your status bar at the bottom. This is exactly what we're doing. We're not just searching for structs, but we're searching for everything. So this is what it roughly boils down to. And of course, this is also why that initial it might go from like 400, it might go instantly from 0 to 400, and then the last 600 crates are going to be super slow, but that's because dependency graphs tend to narrow over time, so there's only so much parallelism available to you. We'd like to do module level parallelism, but that's tricky and complicated, and ask us after. So let's say we do that and we decide, okay, maybe all this parallelism is not enough. What if Rust and parallelism is not enough? So those are often, the low-hanging fruit of performance optimization, but maybe we really need to climb the tree of performance optimization to really unlock what we have here. Which is to say, it brings us to cream, more specifically caches. Apologies to the Wu-Tang Clan, but we will start to introduce caches. And the thing about caches is that caches are great, they're useful, but they're also technically harder than parallelism or rewriting things in Rust, because it now introduces state. And as an example, caches are complicated, right? The first of which is that they introduce modalities. So modalities is a way of thinking of it as like, here's a mode that your system works in. This is to say, like, what happens if your system doesn't have access to a cache? What if the cache is empty? Well, you might not be optimizing your non-cache state as much as you otherwise ought to. If you actually want to read more about this, Mark Brooker of AWS has a bunch of great blog posts about modalities and caching and so on and so forth, and thinking about it. The other thing about caches is that it also requires cache invalidation, which is, one of the very famous computer science problems alongside off-by-one errors, rampant misogyny, et cetera, et cetera, et cetera. But, that's a hard problem, and we still don't have a particularly good solution. So, going back to the original parallel, to like this parallel situation, how would you maybe even introduce caching here, right? Would you maybe throw in a hash map somewhere to avoid recomputing things? You might need to, make the project structure mutable or wrap it in a mutex, but that's kind of gross and it feels kind of unprincipled. And you have this nice pure thing that was going great, and now you had to ruin it with mutation. So, and even if you do introduce mutation, even if you do ruin it with that, you are going to run into a whole bunch of issues of you might forget to mutate it in all the right spots, and you get weird subtle bugs where I changed something and, oh, wait a minute, why is this not actually done? So anyway, this is to say cache invalidation is hard, and we're not good at it. Just consider even a slightly more complicated example here. Let's say someone adds a new struct. Do you want to recompute the entire project, go everything crate by crate, or maybe just do the crate, or maybe just a module? Ross Analyzer, in our case, we can't do it on a crate, but that's, we'll get back to that. So, and the other thing is, what if you have callers of that iterator of structdefs? How do they find out something has changed? As a potential example, we have autocomplete, symbol indexes, and diagnostics are all potential dependents of that structdef. And they all need to find out something has changed or a new struct has been added or removed. So we're only just talking about structs right now, but what about traits? What about enums, function impls, impl blocks, macros? That's a lot. Some of these have more global updates than you would otherwise expect. Could we maybe sort of centralize these updates? Can we do anything that makes it a little bit easier? And the answer is yes. That's actually what Salsa is. It is the best way to think about Salsa. It's an incremental, parenthetical, intended recomputation framework, which is to say it has built-in support for fine-grained caches and cache invalidation. It supports neat features like garbage collection and fixed point iteration, which is really handy for some more advanced type checking stuff, and Lucas will sort of cover that a little bit later. The other really neat thing about Salsa is that it allows you to write code that looks like boring imperative Rust code, but all the caching and invalidation logic is almost entirely invisible. This is great because, if caching a little bit of data, putting in a hash map somewhere, that's easy. But if you have any sort of semi-complicated dependency graphs, all of a sudden you have to let everyone know, but hey, by the way, this thing you're depending on this change, you're going to have to redo your work. Also, the other thing, remember how I said earlier how the first hard thing about caches is that they introduce modalities? I just want to be clear, Salsa will not solve the modalities inherent in caches. That is something that you have to think about in your system. However, Salsa does make it really, does a lot of work through its API, through its idioms, to make it basically impossible for you to express cache invalidation bugs in your program. Rust Analyzer might have bugs. I'm sure some of you have even reported them to us. But we do not really have cache invalidation bugs, and that is largely thanks to Salsa, and I'm personally very thankful that we are able to sidestep this entire large set of bugs and issues. So I just spent a slide hyping up Salsa. Let me actually just show you what it looks like. Same example as earlier. You'll notice it's actually kind of similar to what it was before, right? The main difference, there's a few differences here. The first of which is that there's a Salsa annotation, attribute macros on the functions, as well as on the struct definition of struct def. Additionally, the struct def now takes a tick db lifetime. That is load-bearing and important. We will come back to that later. And the third thing is that you might notice that we're now also passing around a database, a Salsa database around, which is sort of where we store all of the data that we're memoizing and recording and so on and so forth. It's necessary, it's possible to avoid, but it also just makes it a, air quotes, Salsa API. The other thing, so there we go, perfect. The other thing I sort of want to, what are we doing, computer? No, thank you. Cool. The other thing before we sort of continue on, why it's sort of nice and sort of talk about the concepts, is that you may not need Salsa, right? It's really nice, but if the cost of you simply redoing the work when an input changes is less than the cost of tracking everything, caching things, and redoing the work optimistically, you might not need Salsa. It tends to be useful in compiler-shaped stuff where you have deep dependency graphs. A similarity for this is actually UI frameworks. React is based off of the React JavaScript framework. It's based off of really similar principle as Salsa. So when you have anything along those lines and anything potentially deep with deep invalidations or deep dependency graphs, that's when Salsa is useful. Anyway. Let's talk about Salsa's core concepts, and I'll just sort of go through kind of quickly. It's lines and lines of code, and I'll be explaining it. So buckle up. There's two main ideas in Salsa, so you need to think about it. The first of which is ingredients, and the second one is queries. Ingredients, yeah, the name is cute. It's intentionally called that, but it's basically all the data that you have in your Salsa program. And of course, queries are the functions of stuff that what actually transforms data. So let's start with the first, most basic one. This is an input struct, which is basically the boundary between Salsa's world of pure computation. I can't do a good Gene Kelly impression, so you're just gonna have to bear with me here, and as well as the rest of the world. They're not really that interesting, but they're necessary. And in Rust Analyzer, we would represent a file as a Salsa input. The next kind is an intern struct, which is that magical database is back now. This basically, that database sort of implies that lifetime implies that it exists within the context of a database. And the other interesting thing about it is, which is actually interesting that I also have to mention in the context of Rust, but by default, intern structs have partial eq type semantics, which is say if all the fields are equal, then they're considered to be equal. And this is necessary, and we use this we use intern structs in our type checker. This is a simplified version of what exists there, but you might see we have a type kind struct and so on and so forth, but it looks a lot like that. And then finally, we have track structs, which actually have a persistent identity. And we use that, for instance, for our parse tree, for example. Similarly to the intern struct, track structs have a database lifetime, but but basically the equality semantics are a bit different. And the other thing to call out is that these can only be created in tracked functions or queries, which I've not introduced yet, but here we are. Here's a few things to note about them. The first of which is that the first argument is always a trait object implementing the Salsa database trait. That is just a general convention that you see within Salsa code bases. This is sort of where we compute all the state. This is where all the state is, of course, I mentioned earlier, this is where we store all the state and all the memoization happens. The second argument is going to be a Salsa struct, in this case, an input or a tracked function. And then finally, we return a track struct because that's the only place where we can create track structs. They don't typically live outside of your program's computation. you can have more arguments to a salsa tracked function, but those arguments become interned structs, and the macro is a little complicated, but suffice to say, it eventually becomes curried down to one salsa struct or ingredient. It's also sort of important to say what salsa is actually under the hood. So let's say we have this usize input that just has a single field. It is actually sort of becomes a salsa ID, which is really a uthird backed by u32 with an impl block that if I were to expand the macro would be about 400 lines of code, and that's not really going to fit on a slide, but it's a lot of methods, a lot of typecasts, and a lot of transmutes. The methods that you primarily use to access any sort of given data are, there's basically stored within a table with type erased paged allocations. Most of Salsa basically boils down to making those accesses sound via bounds checking and runtime type ID checks and so on and so forth, so that it's, sound. So anyway, that's a lot of Salsa, but let's talk about what Salsa has actually given us. The first of which is fast invalidations. For one, Salsa makes it possible to have really fast invalidations in the case where you're typing inside a function body and not have the rest of the project module or crate be invalidated. It only invalidates the contents of that function. The other thing is that we wouldn't really be able to do is support macro expansion without Salsa. Lucas will sort of cover that a bit better. He's much more of a macro expert than I am. But I don't think it would be possible for us to support either macro rules or proc macros in an IDE without Salsa. And finally, there we go. And finally, it also adds de facto support for firewalls, which is not an inherent property of Salsa, but it is a nice emergent one. So as an example, most of the code that Rust Analyzer sees is incomplete. You're writing it after all, right? Most of it is still being formed. We don't actually lower it to some sort of IR unless we know it's fully correct. Other languages like C++, can have incorrect code to definition because they do code navigation and completion on a syntax tree, which can be incomplete, and their syntax closing heuristics are incorrect. So we're roughly at the halfway mark of the talk. I'm going to let Lucas take over. Segue.
Yeah. Thank you. So I guess it's my time to shine now. Right. So we've talked about what Rust Analyzer currently has done for us. I will talk a bit about what specifically the new Salsa has done for us, as well as what it will enable in the future. A note on all the numbers that you see, like memory usage and times, those are just done against some specific benchmark within the code base. So obviously they will vary from project to project. So, well, what has new Salsa given us specifically? Well, faster incremental updates. So changes in general to a document will now propagate faster than before for completions, for example, hovering and so on. Especially incremental reindexing. So as David earlier said, when you see this small indexing status symbol at the bottom, you always get that when you change your dependencies, for example, right? You add a new dependency or so on. Previous Rust Analyzer or previous Salsa had the problem that we fully had to reindex everything because we kind of discarded the entire state in a way. With the new Salsa now, this is no longer the case. We discard, all the dependencies that may have gone stale, but those that haven't are remain their index that we already computed, meaning we have very big changes in the numbers here from 30 seconds effectively down to 300 milliseconds for adding a new dependency, which is very nice to have. And the other feature that at first we didn't really expect that we kind of needed was fixed point iteration. So when a query ends up calling itself with the same input, you have a cycle, right? So to compute what you want, you need to know what you're currently computing, which doesn't quite work. And one way to solve this is via fixed point iteration. So do the work over and over again until you reach a stable state. So you just assume some sentinel value effectively. Right, and these are some features that the new Salsa will ideally support in the future that we heavily anticipate. So one being safe state. Everyone probably has realized by now, when you start your Rust Analyzer session, it fully has to index the entire project every single time. Depending on the project size, this can take multiple minutes, which is a huge work blocker, right? So ideally, a lot of this work that we do on every startup could be cached to disk, loaded from disk, and then we only need to do minimal work to get back to a running state. Then there's fine-grained parallelism. Right now, Rust Analyzer is parallel for each request it has to process, but for things like completions, for example, that still runs entirely in a single thread because it's a single request. And completions does a lot of collecting of, well, completion items, what do we want to complete, and this is embarrassingly parallel. You can just do this kind of search on multiple workers, right? And the new Salsa will hopefully enable us to do this in the future, which would finally bring down completion times from 500 milliseconds to 50, depending on the project. Then we have garbage collection for intern values. Right now, when we intern something, it is effectively leaked. We will never reclaim that memory. So if this concrete value or the document changes in a way that this value is no longer reachable by anything else, it is that memory that is not going to be reclaimed, which is part of the reason why very long Rust Analyzer sessions tend to use up more and more memory. We are hoping, well, in the future, Salsa will get garbage collection for these kinds of values. So hopefully that is resolved soon enough. And then we have speculative execution, which is a very fancy term. Some of you that may have seen Rust Analyzer source know about this. There's this interesting identifier which is being used in completions. We basically insert this identifier, which used to be IntelliJ rules because of the initial author of Rust Analyzer, and it's inserted to fix up the parse tree. To fix up the parse tree so we can make better semantic analysis for the surrounding context. And this breaks down with macros because macros are weird and special. And so ideally we want to introduce this as a speculative thing. We want to explore the state of the database as if we made this change. This is where this feature would come in. And we would likely use copy and write semantics for it. Yeah. Memory usage is a fairly big problem, as most of you probably know. Especially for the new Salsa, it went from on our benchmarks from 2 gigabytes to 10 gigabytes. Now it's back to roughly 2.3, in part to a lot of work from Salsa contributors and also from the Rust Analyzer team. One big PR from Shoyu Vanilla, for example, halved this regression by implementing a very simple thing that allowed to reuse slots that were basically stale all the time. Then another PR that allowed us to fold enums into an ID or get rid of a lot of logs that were way too fine for what we really needed. This is a snippet of code that shows the structure that Salsa internally uses to keep track of bookkeeping of all the query information dependencies. As you can see, it's very big. This is a big contributor to the memory usage. And so we were trying to think of ways of maybe not having this for every single thing. And as it turns out, there's an interesting path forward. A lot of source code that you use in your projects is read-only, creates I/O dependencies, the standard library sources. You will never edit this. We don't need to track the dependencies here. Once it's computed, it's not going to change anyways. So we can discard all of this information for these things, right? Which we don't know how much it will save, but it's probably going to be a good chunk once we explore that. Right, so then memory management. Obviously, we have all this data that can go stale over time. We also want to bound memory to like some ceiling where least recently use caches come in. So we have X many entries. You now have X plus 1, so you discard 1. So you always like keep X entries in it. That's where this cache comes in. Old Salsa used to evict things immediately while you were still computing, which is not that great because that means you might be in a query, compute some result, do something else. This result now gets evicted again. You call that query again in the same computation, and now you need to recompute it because you don't have it anymore due to the eviction. So instead, what new Salsa does is we defer it to a specific point, this eviction, which means we have a higher peak memory usage until we do the actual like garbage collection again. It's also kind of needed for the TickDB stuff. I unfortunately don't have time to go into in-depth for that. But basically this raises the point of, okay, when do we actually drop these things? We need like some concrete point where we can drop it. And that is where revisions come in. Some point in time where we basically know, now it's safe or fine to like discard things. That's what revisions are tracking, like it's just a generational counter. So whenever we bump the revision, which happens every time an input changes, so every time we type, you bump the revision. That's when you when we can do this reclamation, because now nothing can refer to these things anymore. This does have like one problem. This is like the cancellation point, which needs to be fast. Why? Because when you do completions, when you edit things and you want to produce completions for the given text position, it's an input change. That means it triggers cancellation, and we want to compute the completions as soon as possible after the cancellation ends. But now we drop all these values in the cancellation step, meaning it is a very expensive step, which is not what you want. So there's this common trick in Rust where if you have a lot of destructors running and they slow down your program, you can just move them to another thread. Most of the destructors are just heap deallocations, and so there's not going to be anything. In theory, if a panic occurs, you kind of have a problem, but we just assume that's not going to happen, right? Yeah, we are kind of out of time, so I think we'll just skip that part maybe and do questions.
Yeah, we can just show that quickly, that slide at the very least. And
we had no transition ideas, so yeah.
So
we just wanted to like quickly show a couple of other things here.
Yeah, and we can talk about it.
We can talk about it, or if there's questions, we can also do questions. We are flexible.
Do people want to ask questions? Sure.
Right. Valid question, yeah.
Okay, if you have a question, can you come down to the front?
So when is this going to be available? You said you switched to new Salsa. Is this already...
The version that uses new Salsa is already deployed. It's just like we had a macro that mimics the old API for ease of transition. It's just we need to like phase that out to like use more idiomatic use of the new API. But you're likely already using the new Salsa version.
For the past 2 months.
Very cool.
Yep.
Thank you for the talk. It was very nice. I don't know, somewhere halfway you mentioned a firewall, and I am assuming you're not talking about network firewalls, so what the hell kind of firewall is that?
I can expand on that. So the idea is that like Are you familiar how compiler people sometimes say lowering?
I've heard the term, but I forgot what it meant.
That's okay. The idea is you write a bit of code, you write a code, and then you just transform into a different representation that's more optimized for a given problem you're trying to solve. So a lowering that we might be doing in Rust Analyzer is going from a syntax tree to some sort of IR, some intermediate representation that is easier to do code navigation on or completions on. What the firewall basically means is that we will never actually go from an incomplete syntax tree to an incomplete intermediate representation, because that's just an invariant that cannot be broken. If the syntax tree is incomplete, it will never be lowered, which means that things like autocomplete or go to definition will always be working, because we can't actually ever give it bad data. Is really what it boils down to. We're upholding invariance around correctness.
Okay, thank you.
So, thank you so much for the talk. So my question, from the sheer ignorance, like from utter ignorance, so we know, right, we're in Rust, that garbage collection has some trade-offs, right? Why is garbage collection needed, right? So is there any possible Salsa version that doesn't use garbage collection? It's just I've never, heard about this before, so thank you.
So, I mean, garbage collection is really, it's not like we're doing tracing GC or something like that, right? Or we aren't doing like ref counting in theory either. It used to do ref counting usually. We just do garbage collection now because we have this feature where queries can borrow from the database contents. That's the TickDB lifetime that is like everywhere basically. And that means if a query can in computation depend on, like, have references to the database content, we can't evict this content yet because there might be a reference out there. And that's why we need to wait until this revision bump, because once the revision bump occurs, we know there's no outstanding computation, and therefore it marks a point in time where we can actually drop all these stale values. That is the garbage collection in this regard. Otherwise, we just rely on just whatever Rust does with it, with its ownership system, knowing exactly, the scope ends, we can drop.
Thank you.
Hello, thank you for the talk. I got one remark and one question. First, I noticed that in previous versions of Salsa, you had to do, I think, like a big trait with your database, with methods. I noticed that's not there anymore, so that's cool, because that was very annoying. And you mentioned like there's 3 types of structures, I think, like track structures, intern structures, and value structures. And my question is, input, intern,
and tracked.
Inputs, value, and tracks. My question is, why not intern the values? Like, why is it not just all intern? Or like, at least, why is it not just all intern plus tracked?
So inputs, like input structs, for example, are basically in the dependency graph, you could think of them as the leaves, right? That's the root or the roots, depending on how you view it. That's where our computations start, right? Like inputs have no dependencies by themselves, whereas queries always have some dependency input, unless it takes no input, but then it doesn't do anything, because then it would have like side effects, which is not good. So you kind of need inputs to start your computation anywhere, really. That's like the best I can really say about that story. Whereas like, where was I? Intern and like tracked structs really just have the difference. Interns have no identity. As David explained, if the fields are equal of something you intern, then it's considered the same instance. Whereas tracked structs have identity, so if their fields are equal, they still might have a different identity. They might still be different objects. It depends on which query is creating them. It's very subtle, but it depends on your use case which kind of identity you will end up needing.
To jump in quickly, just as an example, to establish the equality of a tree, it's expensive, but establishing the equality of like a small integer is easy. So, or like the equality, sorry. So parsed, because you have to walk the entire tree versus single value. So that's kind of want to maybe offload that sometimes. So, or skip it entirely. It's a performance trick.
Okay. Lucas and David, thank you very, very much for your fantastic talk. It was really fascinating. If you have more questions for them, I think you can catch them running around somewhere at some point.
Yeah, we'll be around here.
I'm gonna hand over.
Where do we?
So again, we are going to continue the GOSIM Spotlight adventure. For those of you who missed it, these are talks that highlight new and exciting work in Rust that you might not have heard about before. Again, thank you to the previous talk, folks. So we'll start at 5 after. So we've got about, what, 3 minutes or something? 5 minutes here. If you need to rush to the restroom, now's the time. And yeah.
I think this make a lot of sense. I think this should say 8 is my guess.
Yeah, that's my guess.
No. I think cinema rooms need to be cleared by 6.
Oh, I see. Yeah, that makes sense. Yeah, you need about as many users by 6. Yeah.
Okay.
Yeah.
Otherwise,
is a bit slow. Yes, should be this one. So I should be able to. How should I show it? Like via email or?
Via email's fine. My email is bart.massey@gmail.com.
Yeah, network
Or
is
I
not.
can type it whenever, once you get to share here.
Yeah, I should.
Yep, just push the share button somewhere here, I guess. We should be good to go.
Yeah, I just also need to like change the settings for it to be like for it to be able to actually see it.
Well, if you share it by email, I think it'll be all right.
No, actually,
Oh,
there's anyone with the link.
Things going well? Oh, you're just gonna send a link. I was just gonna have you share by email by typing
Oh,
my email right
I can
here.
send either one.
Yeah, either way, whatever you want to do.
Email.
I'm gonna disconnect. I'm gonna mute
That's gonna take
for a
some time.
minute, I guess.
Okay, new email.
Because I don't really want to show my.
Yeah, understandable.
Just pull it out.
Yeah, I was just gonna see if there's some way to
Compose.
blank it.
God, why is it
No, I can just pull it out. It's easier.
Okay. Yeah, you're right. It's easier.
What's your email again?
Bart.massey. Massey. I'll show you in a second here. It's bart.massey like this at gmail.com. Like this. The usual technical adventures we have, but we are all ready to go again with the GOSIM Spotlight and check out some more really super cool new and innovative Rust work. Right now we have Michal Kostrubiec. Yeah, Kostrubiec. Who's sorry, thank you. Apologies.
No problem.
Who's not online is Fractal Fur, which is way easier for me to pronounce, and it is presenting for the second time here at Rust Week. Previously about some work on compiling Rust to C, and now about an extension that compiles to .NET. I think it's super, super cool stuff, and I'm really excited.
Yeah.
So let's welcome Michal.
Yeah. So a lot of the code is actually shared between the C side of things and the .NET side of things. It's technically speaking the same project, but also not really. Like the difference, like I believe a couple thousand lines of code. So I think once again, as I did with the compiling Rust to C, like I think it's important to say why I'm doing this. And like the one answer is obviously for fun. But another is that I'm kind of researching what are the limits of interoperability between Rust and .NET. And my project compiles Rust to .NET assemblies. This is the format that C# and F# compiles to. Really, from the perspective of the .NET runtime, my Rust code kind of looks like some weird unsafe C#. And this allows me to do things like allow Rust code to directly call a C# API. Here we have here we receive a reference to a class, and interestingly, you can actually hold references to .NET classes in Rust. This is like code that more or less works today. I will later have some examples that are a bit more out in the future, but right now you can accept a reference to a .NET class in Rust code. You can call its functions like normal functions, virtual functions. You can access its fields, and the idea is basically to make kind of see how far we can go with interoperability between those two different languages. Because like one of the biggest reasons people don't want to mix languages is the friction on the interop layer, and if we can reduce this friction
as much as possible, then maybe it will be slightly more feasible. Additionally, like since this Rust code is compiled to a .NET assembly, from the perspective of the C# code, really doesn't look all that different from a normal C# function. Like here I use a class named Rust, like as an example. You can later on I will show like the way you can. There's a way currently slightly in progress of you defining .NET classes in Rust. But like if I name this class something different than Rust, I don't think you will be able to tell that okay, this is like something different from like your standard C# code. So that's more or less the idea, to expose as many capabilities of the .NET runtime to Rust code and to allow you to mix them together as easy as possible. So here we have like some of the things that are currently highly work in progress. I am currently seeing how I can use macros and some compiler side tricks to allow you to define .NET classes. Like right now I'm doing something quite weird to do this. Actually this will compile down to a Rust function that gets interpreted at runtime to create the .NET code. Yeah, so that's more or less the goal of the project. The goal is to allow people to write .NET assemblies in Rust and for you to be able to use .NET code from Rust easily. Like as you can imagine, there are quite a few of .NET libraries and like quite a few Rust libraries, and I feel like both ecosystems could benefit from such a thing. For example, like .NET has a garbage collector, which has some overhead, and imagine you may have some large set of data that would live for a couple seconds and then would die. So .NET would actually have to take quite a bit of time to reclaim that. You would have to wait for a major GC pause. And if you write that code with Rust, you could kind of get the memory freed slightly earlier. So that's more or less the idea. Like in cases where it's the performance matters more than ease of use, you could drop down to Rust. And like maybe I will talk a tiny bit more about how this all works. So Rust C code generator is a compiler backend. You can kind of think of this as a compiler plugin. So it can be loaded at runtime. You can actually use this with an unmodified Rust compiler. And as I said, from the perspective of the .NET runtime, there is no difference between Rust and unsafe C#. Here we have an example of a Rust function that was decompiled back to C# because the way the ER is designed, it's designed for you to be able to easily go to the ER, from C# to this ER and back to C#. So here we can kind of see how this would look from the perspective of the .NET runtime. I mean, like you have an option. I have once experimented with translating Rust generics to .NET generics, but I have concluded that it's not really feasible to do this in a way that's both performant and like fully correct, and also looks kind of nice. So for now they are distinguished by the hashes. Like it is a limitation that you cannot share like a generic type with .NET, but you can do quite a bit of stuff on interop. Like to give an example, because the .NET code is just in time compiled, there is really no issue with layout stability, because each .NET assembly contains full information about the layout of a type. You can actually safely send to .NET a Rust type with a Rust layout, and the .NET code will actually adjust depending on what the layout of the type is. So if you recompile that, and if the compiler settings change, if the layout of the type changes, it will change on the .NET side too, which is quite nice, I feel. I don't actually compile this down to C#, I compiled it down to what's called CIL, or Common Intermediate Language, and this is what our .NET assembly contains. You may wonder, like, what is it? Like, it's a form of bytecode. I like to think of bytecode as sort of instruction set for a made-up CPU. So we can kind of think we have an imaginary CPU that executes .NET instructions, and the JIT compiler is actually then responsible for turning that into native code. Here we once again have an example of a Rust function. I believe this one is used in iterators. We have a range here, as you can see. And since we are not referring to fields directly, we are referring to them using this load field address instruction. As you can see, like the layout can actually be adjusted. So that's more or less the goal of my project, and that's more or less what it actually does. So compiling Rust to .NET will hopefully allow for very deep and seamless interop. As I said, you can define in the future you will be able to. The syntax for defining classes is actually not fully ready yet. Like you can define very simple classes, but I want to be able to handle as many cases as possible. So I don't consider it to be ready yet. But you can already like call .NET APIs, construct new instances of .NET classes, so you can actually call constructors and have like full access to GC managed classes. I know there will be questions about how you can ensure safety of that. I have spent some time on getting diagnostics that will detect misuse of .NET features. So, well, I'm not yet confident that it's fully safe. And the messages could be way better because they're currently quite ugly. They will catch quite a few cases of like you misusing misusing .NET APIs. Yeah, so basically this is the goal of my project. I've been working on this for about 1.5 years now. It can compile already most of Rust code, and I kind of hope to, in the future, maybe this will allow for those two ecosystems, the Rust ecosystem and the .NET ecosystem, to be slightly more interconnected. Yeah, so very much like thank you for listening. If you have interested, you can like look at my social. I will also believe be on the kind of the GOSIM spotlight. So I will have a spot there. So if you have any question about compiling Rust to .NET and compiling Rust to C, I will be sitting there and I will be ready to receive your questions. If you don't manage to find me there, you can, or have a question later, you can also, as I said, write to me on GitHub on my social. Like, just contact me and I will be more than happy to talk on this about this project for hours, like, because there is quite a bit of stuff to talk about. Yeah.
Well, thank you very much. That was fantastic. I'm very excited about that work. Yeah, like is the custom for these GOSIM Spotlight talks, because the people will be up on the mezzanine, up above the eating area there. There's a space for the GOSIM Spotlight folks. Please come up and say hi to them and ask your questions and that sort of thing.
Sorry.
So we'll have the usual setup adventures, I'm sure. But in the meantime, I want to introduce Nadri, who contributes to the Rust compiler on all the features related to pattern matching. And as a person who did pattern matching decades ago for a completely different class of languages, I have nothing but mad respect for pattern matching people. So today we'll be hearing about a tool to extract all the types and functions from the crate.
Thank you so much.
This is one of those things that is just going to have an endless pile of cool uses. So I'm very, very excited to hear about it. So we will let me know when we're ready.
Is my screen showing? My screen should be showing.
Well, it's
because it's the previous screen. I don't know why.
No, that's. Oh, I see. You need to move the.
How does that?
I didn't unplug this. It should not be
How
possible.
It must have frozen somehow. On the other end, where's our technician?
Wait a minute. It's frozen. Probably give a second.
Okay. So another second. We'll get out as close to time as we can, and then we'll have a few last second announcements. So please hang when we're done. Oh, a thing is happening. All right.
You don't see inputs?
Laptop is also off now.
No, it's not off. I
Oh,
selected the other screen. I can try again. Yep.
More technical trouble, exactly if we need it.
It's all good. Slides are hard.
All right. Yeah. That's annoying.
If not, we can also send it again to this laptop.
Yeah.
Yeah, I need to do a demo though.
Oh, that is not.
Demo.
Yeah.
That won't work very well.
Okay, let me see in the settings then.
I mean, you will not find my settings. I'm sorry.
In the video set.
Are you on GitHub?
Yeah.
I can pull it down.
This is 4K. Let's lower it down to 1080.
Okay, so it froze again. It will come back in 10 seconds. Yeah.
Yeah, lower it down to 1080. Yeah, that like that. Yeah.
Yeah.
And this one frequency till 59.
Yeah.
Still not decimator, but it's okay.
And now try transferring it again, I guess.
That should be good.
Is it mirrored? Oh.
No, decimator, that's the box, that's should be okay now.
I should have tried earlier.
Did the cable get unplugged on the other end, on the bottom?
No,
And
it's
do
good.
just a mirror?
That's
Oh.
what it's going to turn out to be, is that the cable got unplugged on the bottom end again.
I don't think so. Mirror
Just a-
displays.
just a
yeah.
mirror?
Mirror, and then.
And then still back to, yeah.
What was it? This one?
Yeah.
Mhm.
That's strange. Okay, that's really weird.
Yeah, I don't know what to do. This has worked before.
How hard would it be to transfer your demo to another laptop?
Nightmarish, probably.
Nightmarish?
Yeah, nightmarish. I don't know. Do you want to compile Rust C?
Oh yeah, I know.
It's not that hard.
No,
okay,
not
let's
something we can do in 5
check
minutes.
another level. This is a Chromebook, what is it?
No, it's a framework.
Oh, okay. I think, yeah. Sure.
Let's actually unplug this just in case.
Displays. It should be working now.
That's
also
actually
possible.
That's
honestly.
actually possible. Yeah. Keep.
But when you still don't have video.
Why do I not have video? This has worked for every screen I've ever had. Don't touch.
Let's see. I used to be in television. I don't feel like the mirroring is actually working.
That's fine. It's just the different resolutions. I can try to put it just only on the other screen, but then we won't be able to see anything.
Why don't we go down to 12 by 10 or something dumb like that, 14 by 9 maybe. Oh no, but that's the smaller one. What is screen 1 here? Screen 1 is the laptop. Yeah, we need.
Can you also put both into
And then mirror it.
Yeah, 19 by 10 there, and then we switch to screen 2 if we can figure out how.
You can. There's a drop down here.
Oh, I see.
Just click it. Yeah.
Yeah,
and then mirror it.
And then 19 by 10.
Yeah.
Wherever that is now, I've lost it now. 19.
Scroll up. Yeah.
Okay, I can actually. I know how I can do a demo.
And we can apply it, and this may get us there. Yeah, it didn't say
I can make the demo work. I can just send you the slides.
Okay.
What do you want to do?
I can make the demo work on a different laptop.
Okay, maybe what we can do is swap the talks. I will give you 10 minutes to make it work on here.
Yep.
Yeah.
That's
We'll
good
play
for
with
you.
that. All right. So grab both these laptops and we'll
They're gonna
grab
swap
the third
talks.
one. So we have a change of plans. Sorry, technical difficulties as usual. Let's try
yes.
instead with Josh Matthews if Josh is ready to go. Josh has worked with Rust for 14 years, which probably means he's from Portland and I know him, but maybe not.
Have you turned me off? Can you turn me off?
And Josh is going to talk with us about Servo today, which is something I really need to learn more about. I'm really excited about the new work that's been done on Servo recently, and really am excited to hear what it sounds like. So whenever you're ready to go, let me know, and we'll get going. Thank you for
You can use this laptop to transfer things to.
Do I have it muted?
Yeah, I can hear me.
You're muted? What's the problem?
I'm not.
We're gonna
I can hear myself.
Sure. Is that coming through? Not really.
Okay, cool. Let's do this. Welcome to Servo. So, so the elevator pitch for Servo is that with Rust, we can build better web browsers than currently exist. And this was the elevator pitch for Rust itself back in the early days when Mozilla first started funding it. because they were building Firefox and they said, we know all the ways we can do things wrong with C++. What if we had a language that stopped us from doing that? But that by itself, like building a new language is already an investment, a long-term investment. But if the goal is to then do something with that language, that is a very risky proposition if you need to build the language first before you can even start doing the thing you actually want to do. So obviously, the easiest way to validate that thing is just, what if we build a second browser at the same time? What could go wrong? So, Servo was a project under the Mozilla banner from 2012 to 2020. It was led by there was a full-time team working on it that I led during that time. It was the second oldest Rust project after the Rust compiler, because we were building it at the same time as the compiler. And for the early years, we were actually really influencing the development of the language, finding compiler bugs, and then that sort of, we sort of parted ways leading up to the 1.0 release, when we started asking for things that the language didn't actually want to give us, things like single inheritance or green threads and things like that. So it was a small team, but with a really large community that did a ton of work over those 8 years. It was about 1,200 people that contributed during that time. It was really exciting. And the contribution graph here, there was a ton of activity. We made a lot of really cool progress, but then the team got laid off, and at that point, it wasn't really clear what the future of Servo was, because the Servo that was, we had nightly builds all along, but the nightly builds were in a really weird state, because simple pages with that were heavy on text and images, they worked really well. They looked fine. And pages that use a lot of multimedia content, those also often looked really good, because those were the things that this small team was really focused on at the time. But what's going on? Weird. Okay, so unfortunately there were a ton of pages that looked really bad or just crashed the browser immediately. And that wasn't a super compelling experience for people who were just trying out a nightly build and seeing, hey, what's this flashy new browser look like? And it would just crash immediately. So 2023 comes around, and there's a small team at Igalia, who's a browser consulting company, and they were funded to really focus on improving Servo's layout engine and help maintain the project. And so this actually then really revitalized a lot of the community. There's been a ton of new contributors in the past few years, and the browser is actually getting a lot better at rendering parts of the web than it used to be. And you can see again, there's a huge drop-off in contribution, and it's really starting to get back to levels from its peak. So let's take a look at what 2023 looked like. This was the Google sign-in page. You can see it's a little bit wonky. You couldn't even click the next button. You would try, and it would highlight, and then nothing would actually happen. Nowadays, you can log in. You can actually open up Gmail. You can read through your emails. You can open Google Chat and stuff. It's really quite slick. We're quite pleased with that. Here's the Discover Utrecht website. In 2023, it looked pretty wonky. The stuff was half cut off and positioned badly. Now it looks much more like the website if you open it in another browser. And similarly, trying to open Discord in the version from 2023 just broke immediately. And now you can actually log in and read stuff, and it's pretty exciting that way. It was actually quite hard to find these kind of comparisons because so many pages would crash when I tried to load them in the old version. So 2025, really, the focus now is how can we make Servo something that people actually want to use? And by people, what we're talking about right now is developers who would like to be able to show web content in their applications. We're really not focused on a end user general web browser at this point. We're focusing on, can we build a low friction Rust API that has a really nice integration into existing cargo build pipelines that allows people to get an instance of Servo rendering their content as quickly as possible. So really right now, if you have a GL context in your application, we are really good at being able to show one piece of web content inside of that application, inside of some other stuff you're drawing in that window. What we're going from here is we want to make it really easy to then show multiple different things that are unrelated, so that you have more flexibility in the kind of content in your application. There's supposed to be more things showing up. There's a list of experiments that people are doing with embedding Servo right now. there's a experimental backend for Tauri, the app development framework, which right now, today, the one that you use is using your sort of like native web view for your platform. But they're looking for, can we integrate Servo into that so that you have a browser instance that is consistent across all platforms. We have community members who are experimenting with, can we turn Servo into something quite different, quite radically different, as like a terminal browser, like something like Lynx, for example, that has a JavaScript engine in it, but doesn't actually render to a normal like GUI, but actually just shows you content in your terminal window. We have people from places who are building a port for the Open Harmony OS. So there's a lot of different things being done with Servo. I think there's someone from KDAB here who built this integration with Qt, where you can render Servo content inside of Qt applications. Or Qt? I've never actually said that out loud before, I realized. So I think there's a lot of really interesting experiments now. 2025 really is the year where people are starting to actually be able to use Servo in interesting ways inside their Rust applications. And we're really excited about that. And I said, like, there's so many people working on things in Servo right now. There's a ton of different things that go into rendering web content. That's like, any arbitrary web content. And there's people who have all sorts of focuses here. There's people who are focusing on integrating with gamepads and WebXR. There's people who are really keen on like WebGPU. And like all these new web technologies. There's a ton of stuff happening. It's a very exciting space, so we're really keen on that. So if you want to know more about Servo and how to contact us, we've got a Zulip chat instance where you can ask your questions. The code's on GitHub, obviously, and then we've got some social media that you can also talk to. So yes, and I'd love to talk to you more after all the talks are done.
Oh, man. So, yeah, thank you very much. That was fantastic. And I'm really, really excited to be seeing Servo going again. It's one of those things that I think it was sorely missed while it was in hibernation for sure. Yeah, we're having a few more technical difficulties with slides like one has. Hopefully we'll be straightened out in a minute or 5 here. And in the meantime, please hold tight. All right.
Let's see what we can do.
We got a microphone, we got slides, we're all good to go. Everything's fantastic.
Do we have slides? All right, slideshow. All right. How do I escape this? No, I'll do without. All right. Hello everyone, this is a low-tech demo whereby I send screenshots and big JSON files through GitHub. Thanks for your patience while my laptop didn't want to work. As I have been introduced, I am Nadri. My main interaction with Rust is being a compiler contributor, but as my day job I also do Rust. And today I'll present the project we do at work. I'm building Caron, which is a tool that tries to help you get everything from a crate to analyze it, specifically aimed for semantic kind of analysis where you want to see what code is being run, rather than syntactic analysis where you want to do lints. That we don't do that, we do semantic. And so you run, it's a binary, it's a project, you run it on a crate like cargo, it's called Caron, and it extracts everything into a big JSON file. So I will do a demo, explain some of the things we do so you don't have to do them yourself. Some examples of what we built with it and where the project is at. And now to the extremely amazing low-tech demo. I'm literally, this isn't my test suite now. So hopefully you can read that. Go away here. This is an example bit of Rust code that showcases some of the things we can do with Caron. So normal Rust code, and then let's see if I can get to the output file. All right, two things that Caron does. You will run Caron in a crate. We'll give you a big JSON file. This is the big JSON. Oh, this is too formatted to be legible. We'll see if we can find something legible. Whatever. The point is, I will. Oh wait, the demo, the Caron README has examples. Am I that good? Okay, that's the idea. Yeah, that's why I wanted. So the JSON looks like this. You basically get a bunch of lists for everything that's in your crate. You've got, including dependencies, right? Like recursively, every code that you might need to execute whatever is in this crate will be included. You've got the definitions of types. You've got the traits, imps, and declarations, and the functions. And when I mean functions, I mean everything you need from a function: the function name, signature, function body. And it's all a pretty simple AST. If we had the JSON, I could show you. I guess I could show you the docs if you want to see the AST. I'm improvising here. Here's the docs. Let's see. Will it work? Oh yes. Thank you, Rosdoc. Rosdoc is great. Where's translated crate? Here we go. This is the JSON that I dumped with 30, right? It has the lists we mentioned. So what's a function, for example? Here's a function. Function declaration, what does it have? Item meta is where I store things like the name of the function, whether it's public or not, some other attributes you might have on it. I've got the signature, which is literally just input, output. We've got the body. The body, well, you know, it's all very simple kind of AST. And I've got a pretty printed output, so you can actually read what's in it. Let's see. Yeah. What do we got? My function, remember, that was just a simple function that took a slice of t and debugged every element in turn. Some of the things you can see is, well, this is verbose, but this is precise. This is basically the mir, except instead of having gotos everywhere, you might notice we have loops and ifs and branches. So the control flow is structured. So if you want to, if that simplifies your analysis, that's good. It also, we're trying as best as we can to resemble the code that was written as user code. If you want to translate it to something legible, which is one of the things we do. You can see here there's a call to into iter, here there's a call to next. And like this is a very big name of the function next for this particular import, right? And you can find it if I can scroll it. It's probably one of those, right? It's one of those. The body is not here, but I could include it with a flag. And the last thing I want you to notice is here. This is generic code. The function was generic, right? This is polymorphic code. It's polymorphic in T, and we're making all the trait clauses explicit. All the trait is made explicit. It's basically dictionary passing style, if you know what that means. So when this function is called in the main function, it will be provided the implementations. Where's the main? That's the main. The function is called here, and it is given explicitly, this is the import we use, which is debug for I32, right? So all the traits are explicit, so you always know exactly what code you're calling. Back to the slides. That's not my slides. Where are my slides? This one. Yes, that's my slides. Right. So some of the things we do. The point of Caron is it's simple, and you never have to look at Rust's internals, right? Many projects that want to analyze Rust code have to delve into compiler internals. They're not very well documented. They're full of tricky implementation details, and they're full of tricky edge cases. So what we do in Caron is trying to centralize that work. So we're contributors as well, but mostly me. I poke at the internals, I resolve the edge cases, and you never have to think about it. So some of the things we do, just plain a simple binary, and then the crate that reads, it's just the crate with the types I showed you. It's just a bunch of types, 10 sud. There's nothing fancy in that crate to read the JSON. Simple AST. The semantics are accurate. We're taking the mir, so it's as accurate as Miri would in terms of exactly what we're executing, but we're reconstructing control flow as I mentioned. So we get loops and ifs. That's optional, but that's a selling point. The code is polymorphic if we wanted to. So we track all the traits, which is one of the main crazy things we do. But that's needed if you actually want to know what code is being run. We have someone contributed recently in the last 3 months a path to monomorphize everything. So if that's your jam, we have that. Constants. This is almost not an in-joke, but everyone who's tried to write a Rust C driver will know. I hear some laughs. Constants are a pain in Rust C. There's a bunch of different constants. They can be evaluated or not. Like actually extracting what the expression is supposed to be is a pain. We do that. OCaml bindings for like. It turns out that about all of our users use it through OCaml because the sort of the community that does analysis and verification of code is quite keen, especially in France where I'm from. It's quite keen on OCaml. So we have OCaml bindings. So you can use that. And that's it. That's some of the. We've got more selling points. The point is mainly just centralize the work. So if there's some cool thing that you want Caron to do, you can contribute it, and then we only have to do it once. Some of the things we've built with it. The first is a tool called NAS. That was the origin story of Caron. It was developed at the same time. It's a tool that translates Rust code into purely functional code, specifically for proof assistance, if you know about these. And with the aim of proving code, like safe Rust code only, safe Rust code with the aim of proving, doing like interactive proofs on your code. That works decently well. We've got Eurydice, which translates Rust code to legible C. The constraint being that outputted C needed to be actually committed and looked at least legible enough that someone can see. That looks like the thing we wanted, and it's for big companies. I don't know if I can say which companies, but companies that wanted some good Rust code to be compiled on some targets or like included in some build system that didn't yet support Rust. We've got Rudra, which is Rudra was a project to analyze to detect unsafe to detect like bugs, unsafe bugs in a bunch of crates. That was rather successful in finding bugs, and we re-implemented it in top of Caron because why not, to just see if it worked, and it worked it was very simple. Caron on Caron is I actually used Caron on itself to list all the Rust types, so then I can translate them into OCaml for the OCaml bindings. That works super well. Like Caron is a decent tool for reflection. Like once it fits stabilized enough, I think it might replace Rust.json on some things. I hope it doesn't, but I know people will use it. And the final is a collaboration with Imperial College team to do some symbolic execution of code to detect some UB in a clever manner. And they're pretty happy with it, as far as I've heard. So very quickly, the status is that it works pretty damn well, and it's still a moving target because we're adding more things. Like right now, I was working on adding resolving drops, so we know exactly what code is being run on drop. This is not trivial, especially in polymorphic code. But if I've finished that, then Caron will know. And I don't think any other analysis tool of Rust today handles drops correctly. Tell me if I'm wrong. It's evolving, but people are building on it, and that is good enough for that at the moment. Contributions welcome. Come chat, and come chat to me afterwards if you wish. I've got 5 more seconds, so here's the summary. I poked at Rust C internals, so you don't have to. Let's centralize the effort if we can. This is all obviously open source and funded by public money from France. We love it. Thank you.
All right. Thank you so much for the amazing talk. Thanks everyone for the great GOSIM talks. Really enjoyed it. Also, I'm very surprised we were able to fix that right at the end.
Thank you for your flexibility.
Yes.
Thank you.
Yeah. So we're pretty much finished up for the day here. It was fantastic to see so many people here excited about the Rust language and showing up. I'm still personally amazed about how many people show up to these events. It's not that old of a language, and it's still finding its footing, but the enthusiasm is incredible. There's going to be drinks here at the venue downstairs until 7 o'clock, but unfortunately everyone has to be out of this room by 6 or very bad things will happen. Is there anything I'm missing? Oh yes, and of course on Friday there's going to be a hackathon. There's more information you can find on the website, but it's a full day hackathon. Everyone is welcome. It's free. There'll be free lunch. It should be great fun. Please come along if you're available. Thank you. And yeah.
And the last thing, I think, let's give a big hand to the technical staff and the volunteers who've made this all possible. It's crazy, crazy cool stuff they've done, and we really, really appreciate it. So yeah, thank you, everybody, and we will see you all around tomorrow for yet more adventures. Yeah, we didn't want to forget that last bit.
That's great stuff. Thank you very, very much, man. Fantastic work.
Yeah, sometimes with changing the laptops, there's a problem with.
Yeah, especially when everybody's running.
I asked to the other techs if there's a way to work around this, because normally we have like a converter box for it,
Yes.
especially for this,
Yeah.
for different laptops, and it converts, and
Yes.
it should go well.
But I think it's so tricky as well when people are running random Linux things and MacBooks and
Maybe that,
yeah, you get driver compatibility problems.
Because I saw no issues with normal Windows machines.
Yeah.
Mac was also pretty fine.
Yeah.
The last one I didn't know what it was.
It's random Linux machines.
Yeah.
They'll kill you,